Okay, so the recording is started. Welcome everyone to our Global Meteor Network meeting 2022, and we're going to start with introductions. I'm going to be the first one. So I'm Dennis. I am a postdoctoral associate at the University of Western Ontario in Canada. A postdoctoral associate is basically once you finish your PhD, you get to figure out if you can get a permanent job or not. So it can go either way. You become a professor or you give up and you go into industry. And become an amateur astronomer again. And that's basically where I'm at this point. So I was an amateur astronomer before, and I decided to make my hobby my profession. Okay, so I would love to hear about who you are, and probably to break the ice, I'm going to ask Damir Shagon to introduce himself. Damir, go ahead.
Hello, everybody. I'm very happy and pleased that we are here in so significant number of gymnasts. My name is Damir Shagon. I'm come from Croatia. I live in Croatia all my life. Happy to see that my wishes when I was young are coming true, and we have really exciting times working in Global Meteor Network. Thank you very much.
Thank you, Damir. Okay, so the way this is going to work is just please put your hand up. There's a little button in Zoom, and I'm going to call your name, and you're going to introduce yourself. So who's next? Rob, go ahead.
Oh, Rob Steele from Fraser Park, California. I'm a retired software engineer. I was at JPL for 30 years. I have been an amateur astronomer since I was 14, which puts it like 50 plus years ago. And joining the Global Meteor Network has been just tons of fun, really enjoying my camera and looking forward to this presentation, for which I'll have to watch recorded because I have a meeting, another event going on today. But looking forward to hearing what everybody has to say.
Awesome, thank you so much. Okay, so let's go next. Let's do Paul Rogermans, please. So Paul, we're having trouble hearing you. How about you try to resolve the issue, and I'm going to go to the next person.
Can you hear me now?
Yeah, we can hear it.
Okay.
Now. Go ahead.
Well, I'm Paul from Belgium. I have water cameras running and 7 RMS cameras for the Global Meteor Network. And I will have some presentation later today about what I am doing.
Awesome.
Okay, thank you.
Thank you. So how about we do Alex McConaughey?
Hi, my name's Alex McConaughey. I'm one of, I think, 5 people out here in Southern California. I live in Moreno Valley. Bob Massey has helped us organize ourselves and get coverage. I've got 2 cameras pointing generally towards the east and south over Southern California into the desert, and down to south towards San Diego. And I meet up with Rob Steele, among others, and Bob's, and Robert from down in Orange County. That's it.
Awesome, thank you. So Tomayan.
Hi, Tomayan Dijkema from Netherlands. I'm a software engineer at the Astronomical Institute here, but in my spare time I operate a 25-meter radio telescope. And from the radio side, I've joined the Meteor community last year or 1.5 years ago, and I'm playing happily with the software. And I tried some hardware, but well, I have 1 camera running.
Awesome.
That's it.
Thank you. Peter Ashman.
Hi, I'm Pete Ashman. I'm here in Albuquerque, New Mexico, and I serve as the sort of unofficial coordinator for the New Mexico Meteor Array. I'll be giving some information about that, I believe, on the 3rd presentation in the 2nd session today. Look forward to hearing all of the information from you folks. This has really been a great experience for me, starting a little while ago, a few years back. So look forward to a good conference. Thanks.
Awesome, thank you. So I'm just going to go down the list here. We have Marco Shagon.
Hello, I'm Marko. You already heard from Damir, who's my father, a bit earlier. I'm from Croatia, where I did my bachelor's and master's thesis, and I'm currently doing my PhD in the Czech Republic, in Prague. And my mentor is Dr. Jiří Borovička. So I'm working on analyzing meteor spectra at the moment. But I'm also working on some GMN analysis in my free time. So we will be hearing from me soon today in the presentation.
Awesome, thank you. Okay, so let's do David Brown.
Good morning, or at least that's where it is, what it is here. My name is David Brown. I'm with the Calgary Centre of the Royal Astronomical Society of Canada. We installed 2 cameras a couple of weeks ago, and I thought I'd just see what we've gotten ourselves into. So far, we've just had clouds and snow, so I really don't know if they actually do what they're supposed to do. So thank you.
Thanks, David. Okay, Jan Kiperos.
Hi, everyone. I'm a master's student at Western University in the same research group as Dennis, and I work with Dr. Peter Brown and Dr. Margaret Campbell Brown, and I hope to get my PhD afterwards studying meteors. And I'm having a good time. Happy to be here. Nice to see everyone.
Thank you. Dave Jones.
Hi there, I'm Dave Jones. I live in the southwest of the UK. I've been doing meteor detection through radio and optical for the last 10 years or so, just as a hobby. The last 12 months or so, I've been helping to build the UK MON RMS network, which I've been nagging Dennis and Mark McIntyre quite a bit over the last 12 months. That's all.
Thank you. Piotr.
Hi, I'm Firka. I'm a physics undergraduate student in DCU in Ireland, and I've been working on coming up with some machine learning algorithms to classify false positives and meteors from GMN data.
Thank you. Adrian Bigland.
Hi, yeah, my name is, can you hear me okay?
Yeah, we hear you.
Yeah. Hi, my name is Adrian Bigland. I'm a retired clinical microbiologist. Been interested in astronomy for, well, probably since I was a teenager. Became part of the UK Meteor Network last year with my first camera that Dave Jones built. And I've got my second one here that I hope to have up and running within the next few weeks.
Thank you. Keith.
I think this Case.
Oh, Case. Okay.
Oh, yeah. Hello, everybody. Sorry, I missed. Yeah, from the Netherlands. Joining now the GMN network nearly for 2 years now. With and now running 2 cameras. Planning to put up a third one. And lately find out that my interest is going more to radio astronomy instead of let's say the visual astronomy. So. Yeah, see what's coming up, and nice to see you all. Thank you.
Thank you. Mark McIntyre.
Hi, I'm Mark. I'm based in the UK, and I work with David and Richard as part of the sort of coordinators of the UK Meteor Network. I've been involved in this for several years now. My background is in astrophysics and computation, so I'm writing a lot of Python code. That's me.
Awesome, thank you. Gaetan.
Hi, hi everyone. Gaetan Flam. I live in Quebec, and not too far from Quebec City. It's about 100 kilometers southeast. I have 2 cameras operating, GMN camera, and I expect to be able to add a new one. And we're working with some other people in Quebec to install more cameras to have a better coverage of the sky. So I'm very interested about the subject. So thank you very much for the invitation.
Thank you for coming. Okay, Mark Gatehouse.
Hello all, Mark Gatehouse. I'm from Scotland, right at the south side of Scotland, Gretna. I have 3 GMN cameras also feeding into UK MON. Came out of interest in astronomy, so I was a very amateur astronomer, and like fiddling around with things like Raspberry Pis, and that's how I ended up here. Very interesting though. Good journey.
Thank you. I only have a few people left, so if you haven't introduced yourself, please put your hand up and you're going to pop up on my list and I'm going to call your name. Okay, so the next is Waban, I believe. Waban.
You're on mute, Robin.
Okay.
Yeah.
My name is Robin Boivin. I live in Quebec, Canada. I speak French. My English is very broke. And 3 camera. Okay.
Thank you for the introduction. Okay. Next, I have Patrick Franks.
Hi, yeah, I'm Patrick. I'm in the UK, about 25 miles west of London. I'm a physicist by trade. I work in a national meteorology lab in the UK. But my first degree was physics and astronomy, so I always had an astronomy interest. For my sins, I tried to do astrophotography. So I thought sticking up a meteor cam may be another good idea. They got battered around a bit yesterday in the wind, so I think it will need a new plate part. But nice to see you all, and I look forward to the meeting.
Thank you for coming. Pierre.
Yes, yes, Pierre de Pontier. Do you hear me?
I hear you well.
Yes, okay. So I am living in Belgium, and I joined the network just 1 year ago with 1 camera, and I'm also a variable star observer and member of the AVSO.
Thank you for the introduction. Ken J.
Yes, hello everybody. My name is Ken Jamrodowitz. I'm a retired electrical power engineer. I've been running a 4-camera array here. I have some overlap with Peter Gorell's CAM network just north of here. So we've been able to do a few orbits. Right now my cameras are down. I'm upgrading from 4 cameras to 6 cameras, but I had a problem with the last batch of cameras I got from China. So it's on hold for the moment. Thank you.
Thank you. Howard.
Hi, my name is Howard Eden. I've been interested in visual meteor observations for about 2 decades, been a member of the IMO for a while. I'm an amateur astronomer, astrophotographer, and getting ready to put my first station up, hopefully today.
Wow, that's really nice.
Nice to meet everybody.
Thank you for coming. Okay, Tim Cooper.
Hi, I'm Tim Cooper from South Africa. I'm a past director of the Comet Asteroid and Meteor section of the Astronomical Society of Southern Africa. I've been observing meteors visually since 1973. I started video monitoring in 2019 with a small CAMS unit, and I'm wanting to expand that coverage in South Africa now.
Thank you. And the last one with his hand up is David Bailey. Oh, David, can't hear you. But you are, nope. We can, yeah. you can write your introduction in the chat. Okay, how about that? Okay, thank you. And we have
Dennis, Richard was also waving.
Oh. I'm just looking at the participant list. Could you please put your hand up if you want to? Okay, Richard, go ahead.
Hello, everyone. I'm Richard Kaczmarek. I'm the founder of UKMON, and it's good to see you all. I recognize a lot of faces, Paul, Damir. So I've been doing this for quite a while, and probably met quite a lot of you. And well, we seem to have quite a big network here in the UK. So I'm going to be giving you a presentation about what exactly happened, how we got to this point, and where we're going next. All right, nice to see you all.
Awesome, thank you. And we have Lukeman.
Hi, you guys hearing? Okay, hi all, my name is Lukman from Malaysia, Southeast Asia, and it's midnight here. I'm representing Dark Sky Malaysia, advocating in Dark Sky in Malaysia. I just started my project on Meteor Station here with my fellow friend, Adanam, also here in meeting. Not yet installed and still learning. Hope to learn from you guys. So thanks.
Thank you. We have Simon.
Hello, everyone. I'm a PhD candidate at the University of Bucharest. I'm also part of the Moroi team in Romania, working with Freepon. And I'm looking forward to bring some GMN cameras in Romania as well. Thank you.
Thank you. And we have Craig. Oh, Greg, your audio is all garbled. It's very high pitched. Okay, I believe, no. Could you please write your introduction to chat? Thanks. Okay, so I'm going to switch my video to gallery view just to make sure that everyone who wanted to introduce themselves. Okay, Steve Welch, go ahead.
Hi, my video doesn't seem to be working, but I'm Steve Welch, and I'm also with Pete Ashman and the Global Meteor Network, the New Mexico Meteor Network. I've been an amateur astronomer forever, and I'm still one right now. I actually was a professional astronomer for a very brief period of time, and I've always been interested in. I made my first meteor report to the American Meteor Society when I was like 12 or 13 years old. So
awesome. Thank you. So we have time for one more introduction. If there's someone who's really eager to introduce themselves, please let me know. Hand up. Okay. I think we're, oh, okay. We have Gustav. Gustav, go ahead.
Hello. I am based in Berlin. I joined the network last autumn, and I operate 2 cameras here in Berlin. And I am working on the 3rd one that's going to be in Hamburg. So maybe I'll add 1 more camera here as well. So, my normal job is a software developer. I've been digging into the code a bit, but I don't work so much with Python, so it's a bit of a side thing, but really excited to be part of it.
Awesome. Thank you so much. So our time for introductions is done. If you want to introduce yourself, please do it down in the chat. And now we have to go on with the program. So now I'm going to give a brief overview of what we did in the last year and why the GMN is so important for meteor science. But first, I want to thank you all for coming in such great numbers to our 2nd annual meeting. I'm very happy to see that you made some time to attend this meeting, especially on a Saturday. And before we begin, I just want to say how much I appreciate that you recognize the value of this project and just decided to give it your precious time, helping to build our community of global meteor observers. For those who are attending our meetings for the first time, I'll try to explain what this project is all about. In the following talk, I will explain the scientific reasons why we had to take meteor observing to the global scale and try to summarize the key achievements of the project in the last 12 months. In essence, the Global Meteor Network is trying to merge 2 very powerful forces. On the one hand, it's the rigor of scientific research and the drive to better understand our solar system. And on the other hand, the project is trying to incorporate the enthusiasm and the great value that the amateur community brings to the table. So in this mutually beneficial relationship, amateur astronomers, DIY enthusiasts, and tinkerers, you drive innovation and you perform the task of observing meteors and data collection. And the professionals in this project, myself included, although I was an amateur astronomer previously, we provide direction, purpose, while maintaining the high quality of the collected data. Since its inception, the GMN helped put many new eyes in the sky. So it's not just enough to have automated systems running. Every software just kind of hard codes our preconceptions about what we're supposed to see and only searches for a very narrow set of patterns. So having input from people who know what to look for, and more importantly, to recognize when something seems out of place is invaluable. And that's basically the purpose of this meeting. And I would also like for us to get to know each other better so we can work together in a more cohesive way, put faces to the emails. And the second reason why we have this meeting is education. So as you might have noticed already, we're not afraid to share our knowledge. In fact, we believe that to produce quality research, we shouldn't keep people in the dark. So during the brief existence of the network since 2018, we've seen many occasions where the project inspired hundreds of people to take up meteors as their hobby and get involved. they were helped by the wonderful resources that our community members created. And now I want to thank everyone who worked hard to grow our network. The first part of the meeting is basically going to be me giving a very short presentation about meteor science and the GMN. So let me just put this in full screen here and try to hit it like this. Full screen mode. Okay, so we've all seen meteors. We've been out there, probably we've all seen the Perseids. We spent sometimes long nights out in the dark trying to spot some shower meteors. We might have been freezing out during the Geminids trying to see those spectacular meteors. And you know, from that amateur perspective, at least when I started, my question was always why? You know, why should I care about this? To be honest, when I first started in this, I thought the meteors were a bit lame. It's like, what's it's all about? But I just didn't understand what's really so important about it. And that's the main purpose of this talk. So first, I want to say that we have two very different types of material and phenomena that we observe as meteors. So first, we have pieces of asteroids. These are these big, rocky, you can think of them like big mountains floating in the solar system, that when they collide with one another, they produce smaller particles, and they can be pieces of, by smaller, I mean like hundreds of kilograms. And when they enter the atmosphere, they produce these very, very bright fireballs in the sky, and they can drop meteorites on the ground. On the other hand, we observe meteor showers, and they're just simply dust particles that come from comets. So comets are this kind of collection of ice and dust. And when a comet comes close to the sun, all the dust gets lifted from the surface and then spend some time in the solar system. And then when we literally hit that comet's tail, we see that as a meteor shower. So these are two different things that often get classified as meteors. And this talk is going to split into two parts. First, I'm going to talk about meteorites and fireballs. Part is called Meteoritics, and then I'm going to talk about meteor showers. So, first, why do we care about the solar system? Can we just pretend it doesn't exist and just kind of look at our things on the ground and just say, well, we don't really need to explore space? Well, if we want to exist for a very long time as a civilization, we have to understand the asteroid population, because we know from historical evidence and from even very recent records that we get hit by asteroids. A 1 meter asteroid hits the atmosphere every 2 weeks. So that doesn't really cause any damage on the ground. Just there's a big fireball in the sky. However, a 100 meter asteroid, which can cause a huge regional damage, happens every 10,000 years. So we really want to make sure to understand if something like that is going to happen in the near future. That really shouldn't surprise us, because if we look at asteroid orbits that were discovered using telescopes, it seems that the solar system is just a shooting gallery. There's just stuff is flying everywhere all the time. We see impacts in Jupiter all the time. So that really shouldn't surprise us. However, good news is that in the next 100 years, there aren't any objects that are going to hit us and there are going to be a big problem. However, those are the asteroids that we know of, and there are still a lot of them that are undiscovered. Okay, and the second important thing is that comets contain ingredients for life. We sent spacecraft, they sampled the comets, and we found amino acids. We found basically everything that you kind of need to put together to create life. We still don't know how to do it, but the ingredients are there. So if we want to understand the origin of life, well, we better understand what the initial ingredients in the early solar system were that were able to kickstart life. And hopefully one day we'll be able to reproduce something like this in the lab and understand, if we can see these molecules and these different types of material in other exoplanetary systems, that might mean, oh, okay, there is a possibility of life being created there. So we really need to understand the chemistry better. And second of all, if we as a kind of a spacefaring civilization want to maintain our presence in space, we have to understand the dangers, not just of big asteroids, but also very smaller dust particles. So even these meteors that are a part of meteor showers, they're just millimeter-sized particles, and people are surprised that, yes, meteor shower meteors are just so small, but however, they travel at very high speeds, like 20 times faster than the speed of a bullet. And they have such a high kinetic energy that if they hit a satellite or an astronaut, there can be big problems. So we want to make sure that if we're sending astronauts out in space, that there aren't any big predicted meteor shower outbursts that can potentially cause a fatality in space. And that would be really, really bad. So the first, as I said, the first part of the talk is going to focus on meteoritics. So why it's important to study meteorites, so rocks that survive atmospheric flight. And first thing to understand is that at the top of the atmosphere, the initial mass of some of these objects, small asteroids that enter the atmosphere, can be on the order of like 100 kilograms. And then what survives on the ground is less than a kilogram. So the atmosphere serves as a very good filter to filter out everything smaller than a certain size. And basically everything that's only larger and hard enough and slow enough, otherwise the atmosphere just completely destroys it, will survive and be able to get picked up on the ground. So in our collections, in basically the whole world, we have a total of about 60,000 meteorites. And if you ever find yourself in Vienna, I really encourage you to go to their Natural History Museum. They have the world's largest meteorite collection. Their exhibits are really nice. They will tell you the story of how the solar system forms, because you can actually piece together the story by looking at these different meteorites, and everyone tells us something about it's basically our origin story. However, the first question that many astronomers get, and people who are doing anything with meteorites, is how can you tell meteorites apart from Earth rocks? And it can actually be quite difficult, and there are different ways of doing it. So, if you look at some of these rocks here that I put up on the left side of the slide, some of them kind of look similar. So how do you know? If the meteorite is freshly fallen, what it will have is what's called a fusion crust. So a fusion crust is basically just a blackened surface. And what happens is that when the rock is flying through the atmosphere, the temperatures are so high that the surface of the rock literally vaporizes. And that just kind of chars and blackens the surface. And that's why if you kind of crack open a meteorite, it's going to have this black crust, while on the inside, it might be of a different color. Another way to recognize meteorites is by what are called chondrules. So if you crack open a rock and it has these kind of little spherical beads inside, that's basically evidence that this is not a rock from Earth, because all rocks from Earth simply just do not have chondrules. And if you have a piece of rock and you're really unsure what it is, the best way to do it is to get it analyzed in a professional lab. And the way they do the analysis is they just count up the number of atoms of certain isotopes, and they use oxygen for that and chromium. So they just kind of compute the ratio between the isotope oxygen 17 versus oxygen 16. And for example, in this plot, you can see that basically all Earth rocks have this isotope ratio that's in this very, very narrow range. But if we take meteorites and plot them on this graph, you'll see that they actually vary wildly in this isotope ratio. And that's basically the best way to know if it's really a meteorite or not. And we even have meteorites from Mars. They have a very specific isotopic ratio. And also the reason why we know they're from Mars is that when the rocks were forming, some gases from the atmosphere got trapped in the rock. And then when people analyzed those gases, they matched exactly to the atmosphere of Mars. Which is really phenomenal. So why are meteorites interesting just beyond the novelty? Well, the interesting thing about them is that they are completely unchanged since the formation of the solar system 4.5 billion years ago. So, I mean, try taking a rock and putting it outside in your backyard for a year and see what's going to happen. Stuff is going to grow on it. There's going to be water in it. just leave it there for 10 years and it's going to be covered by dirt and who knows, right? The animals are going to pick at it or who knows what's going to happen. However, meteorites basically are the building blocks of everything. And what's really cool is that we can date the formation time of a certain rock, or in this case, a meteorite, by using lead dating. It's very similar to like carbon-14 dating when you're trying to figure out how old, like, I don't know, some piece of clothing is. Well, we can use lead or rubidium or strontium, similar isotopes, to figure out the age of rocks. And if you take every single meteorite, you will find that they all fall basically almost exactly the same date, 4.5 billion years ago. And that time is basically just very shortly after the first formation of the solids in the solar system. Basically, everything after that was just solar system was just gas. And also, what's fascinating is that so early on, there seem to be present amino acids and then DNA nucleobases. That's all present on these rocks that seem to form extremely quickly during the formation of the solar system. So, you know, ingredients for life were there, but the question is, why did life only form on Earth? And are there any similar circumstances in other solar systems that can do the same thing? So just to back the story up and see where the solar system came from. So we know if you're an amateur astronomer, you've probably seen the Orion's Nebula, you've seen M42, you're probably hunting for other Messier objects. And if you have a really, really good telescope, like the Hubble Space Telescope, you can actually zoom in on some of the stars here. And turns out they're actually protoplanetary disks. They have like a disk of gas around them that looks something like this. And our solar system doesn't look like this anymore. We just have planets, which here in this image are these gaps here, and the rest is just filled with dust and gas. And when the solar system formed, our solar system formed, that got all cleared away. So the next step is basically that you have a bunch of gas in the solar system, and you also have water molecules. And then at a certain distance from the sun, that water is going to start condensing, and that's called the snow line. So basically what we know is, because we have two different types of materials, asteroids and comets, that the snow line in the solar system was somewhere around the orbit of Jupiter. And basically all comets and gas giants, everything formed beyond the snow line, and all asteroids and stuff that doesn't have any kind of water or any ice formed closer to the sun. And by knowing this, by looking at other protoplanetary disks with our telescopes, and by looking at meteorites, we can actually piece together the story of how it all happened. So these chondritic stony meteorites that I mentioned before, they're basically just this unprocessed material. Like, imagine literally like directly condensed from this gas nebula. When it was cooling, it just kind of condensed, like, for example, when water condenses on a glass just by simply cooling it down. And they weren't really changed. So that's basically what the composition of the solar nebula was, more or less. However, we have other types of meteorites: iron, palisite, achondritic. And the reason why we know what happened next is because these meteorites come from different parts of big protoplanets. So as you can imagine, these tiny little pieces were kind of coming together, forming big and bigger objects. And then after a certain period of time, what happened was there were some radioactive elements in these big protoplanets that released a lot of heat and melted the interior of these objects, just like the interior of our Earth is melted. And that caused these different kind of mishmash of things to separate. So all the iron went to the core because it's really heavy, and all the lighter elements, rocks, went to the crust. And then these protoplanets, they crashed together, and they just kind of spilled their guts into the solar system. And some of these pieces end up on Earth as meteorites, and we know, oh yeah, this iron meteorite comes from a core. The reason why we know that is because it has these really weird crystals, and the only way to make iron crystals is to slowly cool down iron by 1 degree every million years, and that's only possible in the cores of protoplanets. And then what we really want to do as meteor experts is to try to piece together which meteorites are pieces of which asteroids. So obviously we have the asteroid belt in the solar system. It's between Mars and Jupiter, a lot of interesting stuff there. And if we look at all the thousands of meteorites that we have in our collections, we can group them together, and it turns out that they all came from about 100 asteroids. So as you can imagine, we have a lot of pieces of the same asteroids. And the big question now is, okay, but are we sampling the whole asteroid belt? Like, are there any parts of the asteroid belt that we just, they don't deliver any material to Earth through these collisions? And that's still a question that we have to answer by doing some simulations and making sure that we know which meteorites come from which parts of the asteroid belt. And also, if you look at this graph, you'll see that the asteroid belt, so every dot here represents one asteroid, has a really weird structure. And that can basically tell us about the formation of the solar system. So you can imagine, like, okay, the protoplanetary disk, every single protoplanetary disk that we observe with our telescope looks kind of like a flat thing and has like a certain distribution of dust. So how do we go from that to something that has this really weird shape? And this basically allows us to make models and say, okay, well, if Jupiter moved this way and then planets were like this, we can recreate the shape of the asteroid belt. And the compositional picture of the asteroid belt is also very important, because it can tell us about where certain things formed and how can we kind of put a certain meteorite into the asteroid belt to say, okay, well, if this meteorite comes from this part of the asteroid belt, then in the early part of the solar system, well, here the temperature should have been higher, or there should have been some liquid water here. And the most interesting types of meteorites are what we call carbonaceous chondrites, which seem to have rich in organic molecules, and they seem to have been exposed to liquid water in some part of their history. And what we believe is that they came from the outer regions of the solar system where it wasn't that warm. So actually the liquid water inside, it wasn't warmed up by the sun. It was actually, again, radioactive elements. When they were decaying, they were producing heat and heating up this rock, which was, you can imagine, like having this kind of rock dipped into water for a very long period of time. And then it underwent what's called aqueous alteration, which just basically means that, like, imagine taking some dirt, putting it in water and keeping it for a very long time. That obviously just changes the properties of those rocks. And that seemed to have been in combination with cosmic rays and solar radiation, essential to creating these organic molecules, that kind of tar-like material that was perhaps used to start life. We're not sure. And scientists are so interested in these asteroids that they're willing to spend hundreds of millions or $1 billion of public money to create spacecraft, launch the spacecraft to go and get samples of these asteroids, and then put them in a lab to really figure out what they are. And again, the two very well-known missions, the Hayabusa 2 mission and OSIRIS-REx. Hayabusa already returned about 5 grams of material. It costs about $100 million, and it's going to change our understanding of the solar system forever. And OSIRIS-REx costs about 10 times as much, and we're still waiting for the results. But I think they sampled more material. We'll know more once it returns in a couple of years. However, there's another way of having a cheaper sample return mission. Instead of sending a spacecraft to an asteroid, well, we can just wait for that asteroid to deliver some material to us through meteorites. And that's what we're trying to do as a meteor network, or it's kind of a fireball monitoring service in a sense. However, to really reconstruct where a certain meteorite came, you need to have cameras to observe its trajectory in the atmosphere. And then once you observe it, you can kind of shoot it back using some equations into the solar system, and then say, okay, well, I have this piece of rock on the ground that I found. I observed the fireball, and I know exactly where it came in the solar system. So instead of spending hundreds of millions of dollars, you spend, well, you know how much you're spending on your global meteor network cameras, right? So it's not that much. So what we are trying to do as a network, we're trying to increase the number of instrumentally observed meteorite falls. And by instrumentally observed, I mean literally just to have it on camera, and it can be nice, well calibrated. Right now, the number is really small. We're talking about 40 instrumentally observed falls, 40 to 50 more or less. And that compares to, the number of meteorites that we have in our collections is 1,000 times larger. So for a lot of them, we really have no clue where they came from, and that's why our work is so important. We're just trying to observe more, and because fireballs are such rare events, we have to have a huge coverage all over the globe just to make sure that they're observed. And finally, I come to the point where I can talk about what the Global Meteor Network did in the last year to help meteoritics and to recover more meteorites. So the first thing that we did in 2021 is we published our GMN methodology paper. So that paper, it basically describes every single method that we use. It describes the software in a lot of detail. And it's basically telling the meteor community that they can take our work seriously. So the next, probably the best, most important part of this paper, beyond just the simple description, is the fact that we developed a new type of astrometry calibration. So what is astrometry calibration? So as I said before, if you have a meteor image and you want to figure out the fireball's trajectory, well, the best way to do it is just to figure out how does that image map onto the sky. And then if you have the view of the fireball from one direction and then a view of the fireball from like another camera, you can figure out its trajectory in space, right? And the issue with previous methods that used to use stars to figure out which direction is which is that they weren't really that precise. And the main issue was that it was really hard to calibrate the distortion, the lens distortion of the camera system. So for example, if you have an all sky lens, like a fisheye lens, that introduces a lot of distortion. So people develop very special methods to do that. Or on the other hand, if you have kind of a narrow field camera, there won't be a lot of distortion. So it's easier to calibrate, but you might have some like weird distortion that's really kind of hard to model. We came up with a universal method that can be used either on fisheye lenses, narrow field cameras, whatever you have, and it's at least 2 times better than anything else before. And I'm going to show you later why that is important for meteorite recovery. So what does that mean in practice? With this improved method and our global meteor network data, it basically means that if we have good observations, we can constrain the end point of the fireball to an accuracy of better than 20 meters. So that basically means is that if a fireball is observed using the global meteor network camera, we can figure out exactly where it ended and then project it down and very accurately predict the fall zone where the rock fell on the ground. And instead of searching a huge area of like, tens of square kilometers, we can just very quickly go with a small team and figure out what the region is very quickly recover the meteorite, which is of utmost importance. And because of the development of this new method, we were able to contribute to the analysis of the Winchcombe meteorite. So the Winchcombe meteorite fall occurred last year around this time in the UK. And the UK is specific because they have so many different types of meteor cameras. They have like these all sky desert fireball network cameras, which use DSLRs and are quite expensive. There are these older analog CCD systems, and they also have free pond cameras that usually observe fireballs. And there was also a global meteor network camera that was installed literally a day before the fireball that was able to catch the end really well, as you can see it in the video in the bottom left. And then using these tools, we were able to accurately reconstruct where it came from. But the reason why Winchcombe was so important is that it was a very rare carbonaceous chondrite meteorites. So remember when I said there are some meteorites that spend some time like dipped in water and they have like amino acids and they might hold the secret to life? Well, it was that type of meteorite. However, the problem with a lot of carbonaceous chondrites that we have in our collections is that they were just fines. What that means is that the meteorite fell a long time ago. It spent a long time in the ground. Water got into it, and there were a lot of issues, and there was a lot of contamination. But with Winchcombe, though, it was recovered within 12 hours in a almost pristine condition. It fell on a driveway, shattered into a million pieces because these type of rocks are so fragile. They're basically like kind of coal-like, and was recovered by an amazing effort by the people in the UK. And because of our efforts, it's currently the sea chondrite with the best determined orbit. We know exactly where it came from. So we're able to combine observations from these all different types of cameras, either all sky or narrow field of view like the GMN, and very accurately pinpoint the trajectory. And what's even better, in the days after the fall, when the search was still ongoing, we were able to very accurately measure the final mass of the meteorite. So in the video, you could see these kind of couple of fragments separating and fragmenting. And there's a method called dynamical mass estimation, where you can actually just kind of fit a line through kind of the velocity over time at the end. And it's basically assuming that the meteorite decelerated enough, there won't be any kind of fragmentation and things. And if you know the speed, the air density at that height, and you assume a meteorite density, you can figure out like how large that rock is when it falls underground. And we estimated it's between 0.2 and 0.5 kilograms. And the actual mass of the recovered rock was about 300 grams. So it was basically spot on. And if high accuracy global meteor network observations exist for all meteorite falls, we would be able to do this with a high degree of accuracy for almost every meteorite fall. And as you can see here, we were able to do this only for GMN observations because all sky cameras were not sensitive enough to see this end. The fireball became so faint that we went kind of below their detection thresholds, but the GMN was still able to see it because of the high sensitivity. And then what we were able to do with this data is actually model the fireball in the atmosphere, figure out exactly how it fragmented, and we derived an initial mass of 70 kilograms, out of which were about like half a kilogram recovered on the ground. The rest just perished in the atmosphere. And this modeling also allowed us to realize that this is the weakest rock instrumentally observed fireball that survived atmospheric flight. So if you look at how other fireballs that produce meteorites fragment, so you can imagine when a rock is passing through the atmosphere, all that air is causing a pressure at the front, a force. And then what happens is that pressure can exceed the strength of the body. So it just kind of crushes and fragments into a million pieces. So Winchcombe was really interesting because it never reached a very high pressure. Just because of the way it entered the atmosphere, just because of kind of a very low entry angle, and it never really disintegrated. So what could have happened very easily if the speed was a bit higher or the entry angle was a bit steeper, Winchcombe could have looked like a very bright fireball, and then it would have reached a height of maybe 30, 35 kilometers. It would be a very bright explosion at the end, and then there would be nothing on the ground. And because of this modeling, we know that this is the weakest, the most kind of pristine, fragile material that was ever delivered from the asteroid belt to Earth. And we're currently working on publishing this work in Science, a big science journal. The next thing that we did is we analyzed the fall of the Novo Mesto meteorite, and Marco Chagon will tell more about this in his talk, but the reason why this was so difficult is because only observations that existed were dash cams or security cameras during the day. And it's really hard to calibrate those very accurately. So we developed a new method where, like surveyors, we mapped out individual objects in the field of view of these dashcam cameras, and we're able to fit to a very high degree of accuracy these objects to the video. and to compute the orbit to, again, a high degree of accuracy, which is what we aim. So that was basically what we did in Meteoritics in 2021. However, we also did some work about meteor showers. So if to go back a bit and try to kind of change the train of thought from meteorites to smaller dust particles, we first have to understand where they come from. So as I said, most shower meteors, they come from comets, and they're very small millimeter-sized particles. Comets are really interesting. They usually come from the outer solar system, and they're just this combination of dust and ice. So if you live in a northern climate, and you know how if you get a lot of snow and at the end of the winter, there's this kind of gross and disgusting dirty snow by the side of the road, that's kind of what cometary material is. We call it like an icy dirt ball type of material. And when they come closer to the sun, just the sun simply heats the surface, the ice starts sublimating, taking those dust particles away from the surface. And then over a long period of time, this comet's tail that goes behind the main body gets carried left and right by gravity of the big planets and also by the solar radiation pressure. So basically over time, what happens is that when, for example, the comet comes close to the sun once and then releases this tail, it's very kind of compact and dense. But every time the comet comes and passes close to the sun, these new tails, or the older tails, just get changed and bended in weird ways. And then you can see that these older streams can sometimes get far away from the main part of the comet and can actually hit the Earth's atmosphere. And that's what we perceive as a meteor shower. So a lot of these tiny meteoroids coming in, hitting the atmosphere, and they all are kind of in parallel orbits. However, if you're an observer on the ground, what you will see is that all of these meteors, it seems to be radiating from a single point in the sky. This is just a perspective effect, nothing else. And we call this point the radiant. And measuring this radiant location and size is very important. And I will describe that in the next couple of slides. So as I said before, those younger streams, those younger comet tails that were ejected recently, they're all kind of held together, they're dense, and they're not really dispersed. So they all kind of look the same. So what happens is that when they hit the atmosphere, our perspective of where they're coming from, it's basically going to tell us, oh, they come from a very small point in the sky. However, if these orbits are kind of older, dispersed a bit, they don't hit the atmosphere in kind of a parallel way, but they come under different angles, this radiant is no longer going to be a point. But if you kind of trace back where the meteors came from, you'll see that they don't always cross in one point, but they kind of cross in different points in different areas in the sky. So older meteor showers that are all more dispersed have bigger radiant areas in the sky, and younger meteor showers have smaller radiant areas in the sky. So why is that important? Let's imagine that you're a spacecraft operator and you're trying to understand if there's any danger to your satellite if your satellite passes through what's called gravitationally focused beam of meteoroids behind the planet. So because of Earth's gravity, if you have a lot of these meteorites coming together, some of them are going to hit the atmosphere. We're going to observe them with our cameras, but some of them are just going to get twisted by the gravity and all focused in kind of one beam behind the planet. So you can imagine then, because of this focusing, there's going to be an enhancement in the numbers of meteors in that beam as is demonstrated here in this plot. However, this enhancement in the number density in the beam is dependent on the dispersion. So traditionally, it was assumed in these models that the dispersion of meteor showers is very low, and meteor cameras were just not accurate or sensitive enough to measure the actual dispersion of meteor showers. However, if the dispersion is a bit higher, let's say on the order of 1 degree instead of like 0 degrees, that enhancement isn't really a problem anymore. So if a satellite goes through that beam, it's not going to get pummeled by a lot of meteoroids. It's just going to maybe not even notice it. So the issue in the past was that measuring this dispersion was really hard, and the GMN puts a large focus on the data quality. And we make really good astrometric plates. If you ever heard from me, I'll make sure that you're producing really good data. And because of that, we were able to publish a paper with our NASA collaborators, where we were able to measure the real dispersion of meteor showers for the first time. And it turns out that for most of the showers, the dispersion is large enough that this gravitational focusing doesn't really significantly increase the impact risk of these dust particles into spacecraft. So for most showers, so we don't really have to worry about that anymore. We also observed several meteor shower outbursts. The Perseids had this outburst that no one really expected, and we observed it using our GMN cameras, and we're currently working on the analysis. And we also observed the Andromedid outburst, which was just seen on the radar. So the GMN had cameras in the US which observed the Andromedids, and we noticed absolutely no enhancement of the rates behind as compared to what the radar observed. And the difference between optical and radar is that radar uses radio waves to bounce on the meteor trails. But it sees much smaller meteors than what optical cameras see. And it basically means that the outbursts are very rich in small particles as compared to larger particles that we observe with our cameras. So the biggest upgrade that we're gonna do in the next couple of months to the capability of our network is going to be computing meteor shower flux. So this is just basically how many meteors are entering the atmosphere from a certain shower in a unit of area over time. And then we can very accurately track how the activity of different showers. And we need that for good long-term monitoring. And I just want to draw attention very quickly, because I'm running out of time, is that Paul Rogemans is going to publish a paper in Meteor News, which is going to summarize the GMN status report in 2021. It was a record year, over 200 new cameras, 200,000 meteor orbits. So keep an eye out on his paper. And that's basically it for me. Thank you for your attention. And of course, thank all to 350 or how many people we have in the network. We're trying to keep a close record of all contributors here. So I'm going to finish here. And do you have any questions? Thank you. Okay, open for any questions here, please, if you have them. If not, can just start our break. Tell me on.
Oh, that's hard. No, I keep people from their break.
No, don't worry about it. We have a few minutes before the break.
Okay. How do you correct for the increasing number of cameras? Because you keep recording more meteors, right?
Yeah. So you mean correct for number of cameras when computing the flux? You mean?
Yes.
Oh, yeah. So computing all the corrections to compute the flux, it's actually quite difficult, and still there are some things that need to be resolved. However, the way we do it is we project the area that's observed by the meteor camera onto the slice of the atmosphere where meteors happen. And we just literally count up the area at the height of 100 kilometers. So I actually do have it in my talk here. So as you can see here, this is the projected area at a certain height. And then we also perform some other corrections like sensitivity corrections, the radiant elevation corrections, et cetera, and then we ask, okay, so this is the corrected area, and how many meteors we observed from this camera that has this area in an hour. And that's basically the flux. Okay,
thanks.
Any other questions? You just make sure to put your hand up, because I think I have 3 screens here. So I can't track everything. Oh yeah. Participant list. We have Patrick Franks.
Yeah, I had a quick one. Just a thought on the meteorite ones. So if I'm right, they're essentially formed from a collision of a bigger body or a breakup of a bigger body earlier. So are the ones we seeing recent collisions and breakups, or are they extremely ancient breakups?
Yeah, that's a really good question. Yeah, so we can actually measure that age. When a meteorite falls, what happens is that when a meteorite is in space, it gets hit by cosmic rays and they cause the creation of some radioactive elements. Literally, the cosmic ray just knocks off like a proton or a proton from the atom, and that basically we know the generation rate of those radioactive elements. However, when they fall on the ground, that kind of gets reset and stops. And then if we measure the ratio between these elements, we can figure out the age of certain meteorites. And for example, for some, the age can be very recent. By very recent, I'm talking about, let's say, tens of thousands of years. I mean, these are astronomical timescales. On the other hand, especially iron meteorites, they seem to be very, very old. We're talking about like tens of millions of years. But most of the collisions, they're not as old as the solar system. So it's, whatever generated these collisions happened, tens of millions of years to maybe tens of thousands of years from now.
So is there a peak that relates to the Great Bombardment?
Yeah, so there are different types of meteorites and meteorite falls. For example, there's ones that are called HEDs, Howardites, Diogenites, and Eucrites that come from the asteroid Vesta. And they're really interesting because Vesta is a differentiated asteroid. So basically means we have samples of its surface, we have the samples of its kind of mantle and samples of its core. And we can actually, so in 2015, there was a one meteorite fall observed in Turkey where we actually pinpointed this one meteorite that came from a crater on the asteroid Vesta, because we were actually able to quantify how old the meteorite is and also how old the crater is on the asteroid surface. So this is the first time it was done, and it's just amazing, almost kind of direct sample return.
It's very impressive.
Yeah, and we want to do that for other objects, right? So we don't have to spend so much money on these space probes.
Thanks.
Okay, so we have our break now until, but I'll continue taking questions, don't worry about it. But just, we have officially, our break is now until 17:15. So that's about in less than 10 minutes from now. And then we're going to continue with Young's talk. But I'm going to continue taking questions. So are there any more questions?
It could be me again. I had another follow-up if I'm allowed. It was, as you're so keen on fireball detections, they can happen 24 hours of a day. So would you like to have the cameras going 24 hours a day, really? Because at the moment, the GM ones are really looking at nighttime, but a fireball is bright enough to be seen in the daytime. So it's worth having them running on that off chance of catching them.
That's a really good question. So for a daytime fireball to be visible, it has to be bright. It has to be, sorry?
Yeah, would that be pretty bright?
So it has to be really bright, brighter than maybe magnitude -14. And those types of fireballs are very rare. So there are some networks that are trying to run their cameras during the day, and I think that's good. However, I would maybe rather try to, just first run some numbers and see if it's even worth doing. And if you do have a daytime fireball, like the Novo Mesto in Slovenia that we were working on, there's going to be pictures of it. And, you're going to have dash cam images. So I think you just kind of have to weigh the probabilities there. That's all I have to say. So right now we're not running during the day. I don't think that the GMN, well, if we had, for example, if we could run the camera during the day and just save a very small video file, then sure. but we currently don't have that capability. I'm not sure if there will be in the near future, at least not officially, but because the software can be customized, anyone can do it if they want it.
Just specific fireball detection that only looks for something rather bright.
Yeah, so for daytime fireballs, you don't really need to have any detection, because when it happens, you're gonna know. It's not an easy thing to miss, because to see it, it needs to release so much energy that there's going to be other effects. There's going to be like an explosion. There's going to be like a ballistic wave coming. It's going to be detected on like seismometers. It's going to be very noticeable. Yeah, so a question from Peter Brackett: for daytime camera, presume you have to be careful not to have the sun directly into the camera. Yes and no, because our cameras already point towards the sun and they're just fine, because the lenses are so small, there aren't any problems. We've been running them like that for years. But if you have like a narrow field of view and that's looking at the sun, there might be issues. Yes, Case.
Yeah. Dennis, can you explain? I heard a story that if a bright fireball is coming in, and you can see it, that you also can hear the fireball coming through the atmosphere, but at the same time.
Yeah.
And that's something not logic, because you should think that the sound is coming later than light.
Yep.
How can you explain that?
Because the sound is not coming directly from the fireball. So yeah, that was a big mystery of like, how is it possible that you can see the fireball at the same time and hear the fireball at the same time? It's not, the sound is supposed to come much later, right? And they found that you can, so the sound is not coming directly from the fireball. Let's make that clear. It's actually electromagnetic waves emitted by the fireball are interacting with your surroundings. So the first thought was, oh, maybe it's just kind of very low frequency waves, like even longer than radio waves, are somehow interacting with the fireball. However, very recently, people have found that the light modulation in the fireball light curve, if it's really frequent, can cause material like fabric to produce sound. And they actually did something similar in a lab where they literally had like a bright LED and a piece of fabric and a microphone under a bell jar. And they modulated this LED like with a high frequency of about, I think, hundreds of hertz. And the light literally interacted with the fabric and produced a sound. And that's why we think that those electrophonic sounds come from.
Okay, thank you.
Okay. Do we have any more questions? Okay, so well, we will start in 2 minutes with Young's talk then. Okay, Young, I think you can maybe start sharing your screen and get ready to do the talk.
Okay, sounds good. Can you see that?
Yeah.
Okay, good.
Start anytime.
Okay, that sounds good. Well, hi everyone. My name is Young Capreas. I work at Western University. I work with Dr. Peter Brown and Dr. Margaret Campbell Brown, and I work in the same research group as Dennis. So I'm just a master's student. This is my research project that I'm going to be sharing today, and I'll be talking about how the Global Meteor Network has helped us to characterize the daytime sextantons, and in doing so, we're investigating the nature of the Geminid meteor shower. So what are the Geminids? The Geminids is the largest meteor shower on Earth. So at its peak, then it has around 100 visual meteors during the peak of the shower, which is a lot. And so its parent body is the 3,200 Phaethon. And we know it's its parent body because it's a close orbital affinity to the Geminid meteor stream. And what a parent body means is that it's the original object that created the meteor stream to begin with. But we have some problems with this understanding here. So with the current picture of the Phaethon and Geminid relationship, we don't really know where the mass came from. And so that's why we're going to be looking into exactly what's going on here. So the problem with the Phaethon and the Geminids is whether or not Phaethon is an active asteroid or it's a dormant comet, also called extinct comet. So basically, if it's an active asteroid, then that means that it's just an asteroid that gives off debris and dust. So in the case of Phaethon, one of the current pictures that we're looking at is that Phaethon is, as it's going around in its orbit, it has a very small perihelion distance from the sun. And so that's small perihelion distance, that causes Phaethon to heat up a lot. So one of the possible ways it could be giving off dust or debris as an active asteroid, is that picture of that, is that just like how the desert floor will crack under the heat of the sun, the Phaethon could be doing that in its closest approach to the sun as well. So after it cracks a little bit, then from the heat, then the solar radiation pressure will push the dust off of Phaethon and put it into the stream. And so this is the current picture today, but there is a lot of issues with it. Namely that the amount of mass that's coming off of Phaethon is not enough in any means to create enough mass to supply the Geminid meteor stream. And remember, Geminids is the strongest shower on Earth, and so it needs a lot of mass to keep that up, to have even been created. And so while we have seen Phaethon kind of give off dust in its closest approach to the sun, it's not enough at all to have supplied it. And so we don't know exactly where the mass came from. So that's the biggest problem with the asteroidal nature view of Phaethon. So the second view of Phaethon is, what if it's an extinct comet? And so what that means is that it was a comet, hypothetically, was a comet when it was creating the Geminid meteor stream a long time ago. But now it's just not exhibiting those active comet characteristics. So it's not acting like a comet at all. So the problem with that is that the Phaethon doesn't look anything like a comet. So it's giving off a blue visual spectrum. So the reflecting spectrum is blue toned, and that's very, very rare for near Earth objects. And it's more, like a Pallas family asteroid, which have blue toned reflecting spectra. And so additionally, the orbit of Phaethon is likely to have come from the main belt asteroids a long time ago. And so that would also indicate that it probably was not a comet. So there's problems with both views of Phaethon. Was it an active asteroid? Is it a comet? Or was it a comet? And, how was the Geminids created? We don't really know. And so the debate about the nature of Phaethon is still going on. And so we have a new avenue to study. So the Geminids and its parent body, 3,200 Phaethon, they've been studied to death. We've studied them extensively. We've gotten all the information we could out of both our observations and everything like that for both the shower and Phaethon so far. And so a new avenue of study is studying the Phaethon-Geminid stream complex, also called the PGC. What that is that it's a collection of asteroids that are believed to be related. So that includes, it's 1,999 YC, that's an asteroid. It includes Phaethon itself, and it includes an asteroid called 2005 UD. So 2005 UD is the parent asteroid of the shower that I'm studying in my master's program. The shower is called daytime sextantids. And so 2005 UD is thought to be a split nucleus of Phaethon. So they're very related as far as we can tell. And so through studying the daytime sextantids, we can learn more about 2005 UD, and in turn, we can learn more about Phaethon and the Geminids and how was that created? Is it an asteroid or is it a comet? We don't know. And so even though the daytime sextantids has been, is related to the Geminids, which is the largest meteor shower on Earth, it hasn't been studied yet fully. So it hasn't yet been characterized, and that's the purpose of my research project. So far what we've done is we've done, well, I'll talk about it later, sorry. Anyway, so it's important that we're doing this now because the Destiny Plus mission is going to be launching in 2024 by JAXA. And what that is it's going to send a probe out into space, and it's going to do a flyby mission of both Phaethon and 2005 UD. So it's important that we're studying this now so we have the framework for once that data comes in, we can use that to really investigate the Phaethon Geminid complex and the nature of Phaethon itself. So by then, I think we'll have the answers. So it's good we're doing this now. Okay. Sorry, let me go back. Let me explain what the daytime sextantids is. So it's a moderately sized shower, so it's kind of strong. It happens in the daytime. And so it's named after the sextants constellation where its radiant is, pictured here on the right-hand side. And so it's moderately sized, so it's pretty strong. Yeah, so it's happening in the daytime. So primarily, we're looking at mostly radar observations of these meteors. Because it is in the daytime, we can't use optical. And so far what we've done is we've studied the duration of the shower. So that's when it starts and when it ends. We've extended those periods of times versus like what was previously thought for the shower. And then we've calculated the radiant of the shower and how that changes throughout the duration. We've calculated the orbital parameters of the daytime sextantids, the flux, the mass index, and the activity profile. We've done that all with the radar portion, and we've completed that. Now we're moving on to an optical portion with the help of the Global Meteor Network. So even though this is a daytime shower, there are a small handful of these meteors that occur just before sunrise, so we can view those optically. And so because there's so few of those meteors, we've had trouble detecting them with traditional meteor detection methods because they don't have much area of space. There's not many of those high advanced meteor detection systems. And so the uniqueness of the Global Meteor Network is that they have cameras everywhere. So with the help of the Global Meteor Network, we have detected 33 daytime sextantid meteors. Sorry, Dennis, do you have something to say? Oh, okay, thank you. Okay, we've detected 33 of the daytime sextantid meteors, and of those 13, we have full light curves for. And so we can undergo optical analysis with those 13. And so with the traditional meteor detection methods, we've only had half meters, and so we don't have the full light curves, and we need that to do optical analysis. So I'm gonna do a very brief overview about what it looks like for us to be using the data in this kind of research. So we need to first, what you guys submit as a community is the video frames. And so how do we get the data from that, and how do we analyze it optically? So first we need to extract the light curve from the video frames. We do that first in a set of 3 steps. First is plate calibration. So we take what we see from the video, from what it's looking at, and we kind of have to tell the computer where in the sky is this. And we have to calibrate it because there's lots of different distortions that could be acting on it, such as vignetting, where it's darker around the edges. And so you can see these red circles are offset from the white stars. These are our catalog stars, and we use those to calibrate the plate. Next, we do astrometry. Astrometry is where we choose where the centroid of the meteor is in the frames that we're given. And so here we have this white meteor, and it has an X. So that's where we've decided that's where the meteor is in that frame, and we continue on. So these little X's mean that those are where it was in different frames. So lastly, we do photometry. What that means is that we tell the computer where what pixels are the meteor and which ones are not. It's okay if we get a little bit of the background in there because the background is subtracted out. So this green color, that means that that's where we've decided where the meteor is. So using that, we get the full light curve. So with this meteor in particular, it had 4 stations that observed the same meteor. And so you can see they're all in agreement in the same full light curve, which is great. So now that we have the light curve, we move on to METSIM. So this is a program where we simulate the meteor using tunable parameters. And so what we're trying to do is simulate the light curve, create this black line to follow the light curve. And we also need it to follow the lag. So this is the deceleration essentially of the meteor. And so we have all these parameters here. So we try different combinations and we need to fit both of these parameters. And then we can say, this is the bulk density of this meteor. And so that's the important part. That's what we need to compare the Geminids and the daytime sextantids. And so that's the end of my presentation. So in conclusion, by studying the daytime sextantids, that will allow us to figure out the origins of the Geminids and the Phaethon Geminid stream complex. And thanks to the Global Meteor Network, we are able to optically analyze the daytime sextantids. That would not have been an option had the Global Meteor Network not been there. So thank you.
Thank you for a great talk. Okay, do we have any questions? Make sure to put your hand up and in Zoom, and I'm gonna call your name. Or chat. Great talk. Okay, well, it seems that we don't have any questions. Thank you for your talk, Young, and I would ask.
I have a quick one if I can.
Oh, there's a question.
Sorry,
Go ahead.
it's me again. Sorry, my work hat was kicking in. How many parameters are you fitting in that fit? How many variable parameters are there?
Let me pull it back up. Let me show you. So in this METSIM calculation, so there's only around, I want to say 9 that we actually touch. We're changing for each of them. Yeah, so it's 1, sorry, let me count them right now. 1, 2, 3, 4, 5, 6, 7, 8. There's really only 8 parameters that we're touching when we're trying to recreate this light curve and the deceleration.
So it's some global minimization fit?
Dennis would be able to tell you. He wrote this.
It's done manually. Okay. It's really hard to do something numerically because the model is really not well behaved, but we're working on a way of getting.
It's going through my mind.
Yeah, it's a huge problem. But we can discuss more about it at the Q&A.
Yeah, it'd be interesting. Thanks.
Yeah, no problem. But for now, I have to ask Marco to get ready to present because it is time. Thank you.
Thank you.
Looking good.
Okay, so hopefully you can all see me and hear me. Okay.
All good, go ahead.
Okay, so hello everyone. My name is Marco Shagon, and today my topic of discussion will be the Novo Mesto meteorite fall, which occurred on February 28th, 2020. As you can see from the list of names under the title, many people contributed to the analysis of this event, and the full analysis is much longer than what is presented here. I will today talk about how to use dashcams for science-grade analysis of similar events, as that is the part that I was mostly involved in. Okay, so since the event occurred during daytime, it wasn't captured by any of the meteors of the network cameras. We gathered 9 observations consisting of dashcam recordings, security cameras, and the GoPro camera from a cyclist who just happened to be at the right place at the right time. So most of the recordings have different frame rates, different resolutions, fields of view, as well as different grades of distortion. Some of the cameras were also in motion. So because of this, we needed a different approach than usual for the calibration of the recordings. So the main aspects of daily fireball analysis were presented in a paper by Dr. Jerzy Borowiczka, and that paper covers the basic approach to calibrating the field of view distortion from additional images. And it also points out the main considerations needed to get precise measurements. So having an accurate camera position at the time of observation is key to getting good results. The absolute accuracy of the geographical coordinates of the camera need to be within a few meters. In order to obtain results with a precision of 0.1 degrees, which is something that we aim for, accurate distance measurements are needed. But how exactly accurate do we really need to be? Well, that depends on the distance of the points of interest. The closer the point of interest, the smaller the error in distance which can be allowed. So here you can see a table of the allowed displacements of the calibration camera given different distances of points of interest. So if possible, the calibration images need to be taken from the exact position where the observing camera was. And in cases where that is impossible to do, it should be placed as close to it as possible. And then the azimuth and altitude values of the points of interest should be recalculated to account for that displacement. In Dr. Borovichka's paper, the trajectory is computed from the azimuth and altitude points. However, an alternative approach is to calculate the right extension and declination values from those altitude and azimuth values. And these can then be used in calibration software such as SkyFit. And this is exactly what we started with in our analysis. So the calculated right extension and declination coordinates of the points of interest were used to create a fake catalog of stars from which the distortion parameters were determined. On this image, you can see adjusted positions of some of the points of interest for one of the cameras. In cases where the observing camera is in motion, things are much more complicated. The available points of interest are quite close, and the camera position with centimeter level accuracy is needed, which isn't possible to do in most cases. So to get around this issue, we switched to using geographical coordinates, namely longitude, latitude, and elevation relative to sea level. When using geographical coordinates instead of altitude and azimuth, it's possible to use images taken from other nearby locations which observe the same points of interest and from which a centimeter level accuracy in position can be achieved. Or alternatively, the camera's optical distortion can also be calibrated on a completely different set of points, as was the case for one of the cameras we worked on. So in order to obtain accurate geographical coordinates of the points of interest, on-site images were taken containing stars for orientation. And such calibration images were taken from two angles using DSLR cameras placed at accurately determined positions to allow the triangulation of points of interest within centimeter level accuracy. So this two-location analysis was also done in SkyFit. When measuring celestial coordinates of the points of interest, we paid attention to not include refraction. And from the measured values, the positions of the points of interest on the sky were calculated for a given point in time. And these were then used for the distortion calibration. A frame from the video with the best distribution of points of interest is then selected for the distortion calibration. And once we have a precise calibration, the position of the camera for the subsequent frames is determined by refitting these points of interest and changing the field of view and orientation of the camera, but while keeping the distortion model the same. So up to now, the points of interest used for the analysis, such as buildings, trees, or traffic signs, were all relatively close to the camera. However, the fake star catalog approach can also be useful when using clouds as points of interest, though it needs to be said that that can only be done with low-speed clouds, which remain basically of unchanged shape for the whole duration of the meteor. But as discussed before, the more distant the point of interest, the larger error can be allowed in camera position determination. So when at all possible, we prefer to use distant objects such as stars for the calibration. Then it doesn't really matter if we're not exactly sure to a centimeter where the camera is located. With this in mind, we came up with the idea of using mountain ranges. To our knowledge, this method was not used in any previous analysis of this type. But the general idea of the approach is to find the geographical coordinates and elevations relative to sea level of all the highest visible mountain points in the image. There are commercially available tools and software which are capable of doing this, one of them being the viewshed option in Google Earth. However, none of the ones we encountered provide the option to export the data in a sensible format, or they only work for a much smaller radius around the observation point that is needed for our analysis. So to tackle this issue, we came up with the idea of using an API service to obtain elevation data for geographical points. Thank you, Dennis. After trial and error approaches, we constructed a program which generates equidistant geographical points along a given azimuth in a given distance range from a given point. And you can see here what this looks like. So the coordinates are given to the API service to get the elevation data, and from which the Earth's curvature, taking Earth's curvature into account, the points at the highest elevation are calculated for each of these azimuths. So we can either select some azimuth range, which we want to cover, or we can take individual azimuth values and just find the highest, with the point with the highest elevation there. And finally, we end up with a bunch of these points, which are our new points of interest. And here is what it looks like represented in Google Earth. So the calibration obtained exclusively using this method can depend vastly on the landscape and the meteor position on the image, because while the mathematical fit along the part of the points is really good, it doesn't mean that the rest of the image is well fitted, since all of the points are concentrated in only one position, only one section of the image. So where there are no alternatives, this method by itself can serve as a good first approximation of the model. However, it's best used together with other methods to confirm the quality of the fit and also to give some additional restraints on the fit model. So finally, combining the observations from all of the stations, we computed the trajectory, and the trajectory fit errors were within 100 meters for the nearby stations and about 300 meters for the distant observer in Italy. And together with dash cams, we also used 3 fixed security cameras in southern Croatia, which were somewhat easier to calibrate, and they also give some credence to this trajectory solution. On the left image, you can see the total spatial residuals for the computed trajectory, while on the right side, it's just the positions of the observing cameras relative to the meteor trajectory. And in conclusion, using the Novo Mesto daily fireball as a case of study, a new method of calibration for dash cams and security camera videos of fireballs was developed. And it can be applied to future cases with relative ease through an open source software, which was made publicly available at the following GitHub repository. Also, as mentioned, the mountain ranges can be used as points of interest. However, it needs to be kept in mind that they're not very reliable by themselves. For the meteor position, a bit separated from the portion of the image where they're located, and is best used together with different methods. And also, it's very important, I haven't noted this before, I'm sorry, but it's very important to remember that obtaining the original recordings of the event wherever possible is crucial. So YouTube or other sites' compression algorithms degrade the video quality very much, and it should be, the original video should be obtained. So thank you for your time, and thanks to everyone who contributed on the project.
Thank you for the talk. If anyone has any questions, please put them in the chat. And thank you, Marco, again. And now we have Fiaker with using deep learning to classify geomin data as meteor and non-meteor detections.
Oops. Yeah, okay. Hi, my name is Fiaker. I assume there's a little black box in the top right corner there. That's just a little glitch.
We can see the talk, no problem. Thank you.
Yeah. Okay. So I've this is my thesis for my final year undergraduate project that I've been working on. Is just this machine learning project on global meteor network data. And so the whole purpose of this is that the current GMN algorithm that is used, you get a number of false detections from planes and bugs and clouds. And so the machine learning algorithm would hopefully reduce these false detections by a considerable amount. This sort of stuff has been done before by Peter Gorell. He did a shallow learning neural network for the CAMS network, which is another meteor detection network, just with slightly different hardware. When he did it, he had 100,000 confirmed meteors and 100,000 false alarms as part of his original data set that he could train on. And he managed to achieve greater than 99% accuracy. And then he was able to apply this to GMN data and achieved 97% accuracy. However, at the time, the GMN dataset was quite small. And so then even last year, there was efforts made by another student called Esther Gavin, and she had quite a small dataset of GMN images, but even from that, she was able to achieve about a 90 or 86% accuracy. But then for comparison, the data set that I used, I have a total of 86,000 images with about 59,000 confirmed meteors and nearly 28,000 false alarms. And I'm just going to go kind of over the results that I'm getting. But to start off with, for those of you who have dealt with machine learning before, this is the sort of structure that Peter Gorell used in his convolutional neural network that he had. And I used quite a similar structure for pretty much all of the stuff that I was doing. For those of you who don't know any sort of machine learning, it's not overall too important about this, but I just thought I'd include it there for people who have done the machine learning. So the sort of input data that I was putting in, kind of for those of you familiar with the actual data that you're getting out of the cameras, you get 4 images from it. You get the max pixel, average pixel, max frame, standard deviation. And essentially the images that I was getting out were just, you can see the detections here. I was cropping out these detections out of the max pixel image and subtracting the average pixel image so that I just get the pure meteor detection and there'd be no stars or dust or anything in the background. And then I did also do the same thing with the max frame image, and this would essentially just encode the time information. I'm just going to leave it at that because I don't have time to explain more about how the max frame image kind of works. But I did end up with essentially 2 image data sets, one of just the picture of the meteor and then the other of the time information of the meteor. So when cropping these images, I did kind of, when I started off looking off qualitatively at them, I kind of noticed, you can see here on the right hand side, I've got 3 images here. This column on the left is confirmed meteor detection, and then these 2 columns here on the right, this one here is a plane, I believe, and this one here is a cloud. So when I was going through the data qualitatively, just looking at it, cropping it out, the sort of areas that I was taking from that I knew where the detections were given to me already in text files. And so I could just crop out that exact area. And you can see like this is cropping out the exact area. But I noticed just that some of the fainter meteor trails were being cut off just because they were kind of out of bounds of the detection algorithm. And so I decided to give kind of plus 20 pixels on each side of the image, just so that would hopefully include these meteor trails. And that's where you're getting these images here in the second row. And you can notice there's a significant difference between this first row image here and then this second row image here for the cloud in particular. So you can see just this small area here is kind of just this teeny tiny area here. And notably, this actually made a considerable difference on the performance of my neural network. So these 2 graphs here are just graphs of the accuracy of my neural networks that I was doing. So on the left-hand side, I was feeding in the data that had the plus 20 pixels on either side. So it was including the trails and slightly larger versions of the clouds. You'll notice that the scales on these axes don't match up. On the left-hand axis, it's like 95% to 98%. On the right-hand axis, 67 to 68. And then you'll notice that essentially the performance on the data set that didn't have the plus 20 pixels on either side just was significantly worse, consistently getting the 67.8%. I think this was as a result of some of the cloud detections, because they were so small and so narrow, they kind of appeared just like streaks in the image if I didn't include the plus 20 pixels on either side. So that made it look quite a lot like a meteor. just to point out for those of you who don't do machine learning, the training accuracy here, the blue dots, that's just the accuracy on the training data that I'm feeding into the machine learning algorithm. And then the blue line is what's called the validation accuracy. And that's kind of a more accurate measure of how the machine learning algorithm would perform on real world data that it hasn't seen before. So you can see I was kind of getting a sort of 96.5% accuracy on real world data. I then tried out feeding in the max frame images, so the time coded information. And you can see that in the graph on the right hand side, but it didn't perform as well as just the regular sort of the movement of the, or sorry, just the detection didn't perform as well, only getting about 94% accuracy. And that's dropping off quite quickly after that. And that was kind of consistent over a couple of runs doing that. And then even going on further than that, I tried out different configurations of the network to try and see if I could improve the performance of the network. And I found that even making a much smaller machine learning algorithm, less complex one, with about half the number of variables in it, I could achieve similar levels of accuracy with the sort of 96.5%. And so I think that would be kind of a key thing, that if you're going to try and input this into the actual pipeline, that if you were to distribute this to people at their actual recording stations, that it be as small as possible, and so that the pies and stuff that it's running on aren't completely overwhelmed if it's able to run on them. But I'd need to test and see if that would be able to, or if that would be something feasible. And just kind of suggestions on things that could be improved on at the most, that I can see at the moment, was that like you're getting most of the performance increases from any sort of pre-processing on the images that you're doing. So varying the amounts of border around the detection could be something that could improve or decrease the performance of the machine learning algorithms. And then also for images that are occurring on like the edges or in the corners, I was kind of just adding on extra black around that so that the detection was occurring in the center of the frame. But for things like the clouds, you'd have mostly white across the whole image. So it might be worthwhile to try and mirror parts of the image or fill it in with the average value or something like that. And that's it.
Thank you very much. Okay, do we have any questions? Let's see if I have any hands up. So we have Talian, please go ahead.
Since the value of 20 seems to make such a big difference, did you try any other values than 20?
No, I did not yet at the very least.
Okay.
Okay, any more questions? Simon.
Yeah, have you tried to work with the raw values from the fit? To train the algorithm with the raw values?
No, I haven't tried that, just because it's kind of, the way I'm doing it is I'm cropping out the detections and converting that to PNG files, just because there's functionality available in Keras, the machine learning software, to do stuff quite easily from the PNG images. And I don't really have the time to be adding on a lot more stuff to go from the fit file straight into the machine learning algorithm, just until my thesis is finished, at the very least.
Yeah, because I asked because I've noticed some increase in accuracy by working with the raw values.
Okay.
Thank you. Okay, any more questions? Well, if not, I have one. So we've seen the accuracy, but is that what's the precision and the recall? So basically what I'm interested in is that we don't care too much about maybe including a little bit of false positives, but we don't want to miss any meteors. So can you try to optimize that for maximum recovery? And yeah.
Kind of, I was having some problems previously just with, I had some duplicate images, and so a lot of those results I'm getting were just from yesterday and today, this morning. Okay. I haven't had the chance to do the proper recall on that and see the true sensitivity. But before, I was getting a false positive when I had the duplicate images, I had about 10% of my images were appearing as both meteors and not meteors. And I was getting a false positive rate of 30% and a false negative rate of about 0.6%.
Okay, that's pretty good. Okay, any more questions, or should we? Okay, Tamian, go ahead.
Yeah, just one thing. I look very much forward to this being implemented. Because I also submit my data to the comms network, and they require that every meteor be manually confirmed. And just 2 days ago, I had a night which had 1,900 detections.
Yeah.
So sometimes I go through 200 meteors, and there's two real meteors in there, and the rest is false positives. And this 1,900 was the first night I thought, well, okay, just forget about this night. It's all. I'm not going to through that batch. That's an exception, by the way. You see very fast clouds, but I really need a good detector.
Yeah, hopefully it should work out quite well.
Great.
We need to make sure that the code is made open source on GitHub, and
yeah,
I'm sure that Tamian would love to look at the code and maybe play with it a bit more. Okay.
Not sure.
Not sure.
If it just works, that would be nice.
Yeah, right. Great. Okay. Anything else before we start our break? Well, I think we can just actually start our break. And if there are any questions, or so feel free during the break just to, if you have a question for anyone, just unmute yourself if they see that they're there. I will not be here for maybe the next 10-15 minutes, but I will return after my lunch. So I'm gonna just share my screen and put the schedule up with the time so we know when to come back. And that's it. Okay, see you guys in about 20 minutes. device. Pedro, please go ahead.
Do you hear me? Can you?
Yes.
Okay. Okay.
Your screen. Thank you. Go ahead.
So I will introduce you the MOMET device, a device that allows us to set up 10 mobile RMS stations for the 2021 ARIDS Meteor outburst that we create in collaboration with all the people that you can see below, including myself. I will talk about the motivation, the hardware and the software inside, the observation campaigns and the results from it. And finally, I will talk about the ongoing work and the future. First of all, why do we choose to create a MOMET? As we all know, meteor shower outbursts happened every year, but the orbital geometry or the weather may prevent the observation. So we need to bypass this issue, transportable observation solution. And that's why we create MOMET, which stands for Mobile Observation of Meteors. The MOMET suitcase looks like this. There are 2 wide field of view cameras and 3 narrow field of view cameras inside, and also a grating for spectroscopy. There are also 5 single board computers that allows to turn each camera into an RMS station, because the RMS software runs inside on these single board computers. There are 2 MOMET cases that have already been built, which allows to set up a double station observation that allows to gather more informations like 3D trajectory and so on. About the hardware specifications, the cameras are equipped with a sensor IMX274. The brands are Basler or DMK. We can orient the cameras. There are 6 and 12 millimeter lens with an F number of 1.4. The single board computers are Odroid EQ4 or Raspberry Pi 4. The Odroid runs Ubuntu 20, and the Raspberry Pi 4 runs Raspbian. There is a GPS antenna to gather informations about the location and the actual time, and the bubble level for the horizontality. All the case mechanics, electronics, and power supply has been built by the Modern Observatory. Each suitcase weighs 15 kilos with a power consumption of about 150 watts, which corresponds to 8 hours of from a car battery. About the software, the detection of meteors is performed by the RMS software written by Denis Vida and his collaborators. The acquisition is performed by the GStreamer software with the Aravis plugin. There is a DHCP server that allows all the cameras to connect together and all the GPS also, in order to exchange informations, which allows to create a user interface where we can see the live stream, the point of view of each camera. That helps us to point point the instrument to the right spot in the sky. We can also see the GPS time and location, the RMS software logs, and we can configure the RMS software directly using the interface. During the development phase, we faced some issues. On Odroid, for instance, we faced issues about the low memory that we fixed by creating a temporary swap, which is a file that we write on an hard disk, and that acts like a random access memory. There was also an issue about the camera driver installer, which can't run on Odroid. So we create our own custom installer. And finally, on Odroid, it was also random disconnections from the camera that we managed to fix by limiting the bitrate of the cameras. There are a lot of dependencies to install, so we write a script that performs these installations automatically. Only one software can take the control of one camera at the same time, and there are two softwares that use the camera. It's the live view software and the RMS software. And to avoid both softwares trying to access to the camera at the same time, which will not work, we choose to let the live view software to take control of the RMS software execution.
2 minutes.
And finally, there was a problem about the default driver, which is video for Linux, that can't handle the GenieCam cameras. That is a protocol that is used by the cameras that we use. And to fix this issue, we use a Aravis library for the live view software and Aravis plugin with GStreamer for RMS software. We set it up a double station observation at Chile. Between both stations, there was 50 kilometers. One was located at the LCC Observatory, while the other was located at the Mamayuca Observatory. Here you can see pictures of the setup. Here you can see pictures of that night where we observed the arid meteor shower for the first time. Actually, the processing is still in progress. We are trying to master the softwares in order to get the data, the results as accurate as possible. There is also one result calculated by Denis Vida about the trajectory and the orbit, but further study is needed. And about the tensile strength, we are currently working on the calculation of that information. During our after the release of the suitcase, we received some feedbacks that asks us to create lighter suitcases. we want to create a third suitcase to guarantee a good geometry by June 2022. The future, we plan to perform an observation of the Tau Hercules on the 2022. Any collaboration is welcome, and you can ask to Jeremy for more details about how to collaborate to this observation campaign. Thanks for listening.
Thank you. Okay, do we have any questions? Okay, well, if someone does have any questions, please write them in the chat for Pedro. Thank you again, Pedro. It was a wonderful talk, and I hope we finish analysis soon and publish a paper about the ARIDS. So one thing probably wasn't, probably some people don't know, but the ARIDS are an amazing meteor shower because there was the first time in history where a comet was discovered. Meteoroids were released from the comet, and then we knew where the meteor shower would happen before actually happening. And Pedro's team built these instruments, took them to Chile to actually observe this unique meteor shower. Thank you again. The next up is Tamayan. So please go ahead. I can see your screen, but we still can't hear you.
I will just unmute. That'll help.
There we go. All good. Go ahead.
Okay. Do you see the presenter screen or the other one?
The good one.
The good one. Okay, thanks. So this is about an observation of last week, 19th of February, 9 days ago. It's not a meteor, it's a satellite burning up in the atmosphere, but that gives trails that look like meteor trails in a way, or like fireballs. And in fact, it's a Starlink satellite that burned up above Spain. So there was some talk on the mailing list also about Starlinks burning up. That's a different batch, but I'll show a video of that because it's so cool. So this is another network, but you see a Starlink satellite here, and you see here a bunch of Starlink satellites burning up above Puerto Rico. And this was actually a failed launch. This was launched 2 weeks ago or so. And because of a geomagnetic storm, they failed to get into orbit and burned up. I think they think this were two Starlink satellites burning up. Our re-entry above Spain was a bit less spectacular. The Starlink satellite itself is about 3 by 2 meters and a huge sun panel for energy. Starlink is a system to bring thousands of satellites into orbit. Let's not go into detail about whether this is useful or a waste of space. But it's nice to see them burn up. I was triggered by this YouTube video which was published the day after the re-entry already. You see here, I think this is a WATEC video from the SMART project in Spain, which is another Meteor Network. And they filmed this re-entry, published it the next day, and even published the trajectory, very nice. And I thought, hey, we have Global Meteor Network cameras in Spain. Let's have a look if they caught it as well. So I quickly checked all the stations that were ISTRA stream and found a couple of examples there. I sent out an email to the groups, and immediately or next day or so, 5 people responded that all had saved the FITS files with the recording. So here you see the nice trail. This is a stack of 3 or 4 FF files. So that's in fact 30 seconds or so. So this is a fireball that lasts very long. It moves quite slowly. And another few cameras where you see the fireball or the trajectory, the thing burn up. It looks like it's hitting this chimney, but the trail goes along a little bit further to the left. Here's a video or reconstructed video from one of the stations, which I think looks very nice. This is reconstructed from FF files, but in the middle an FR recording, so that's a more video recording was made. You see it nicely there. I'll zoom into that segment, and here's another FR recording, but the FR recording, the FR detector got the speed of the thing wrong, so it's not a very nice one. But so zooming in on that one segment where you do have the video recording, you see here three. Well, let's just look. Here you see the satellite and two pieces that already broke off of the satellite and move a bit in front of it. You see, in fact, there's four separate pieces. This is slowed down a lot. And if you look at this, there's 3 stars here, and those 3 stars, these segments are 7 kilometers apart. And you see here, what surprised me a little bit is that you see this Mesartim star seems to go away when the satellite passes in front of it, or the satellite trail. So we're not in fact looking at a burning satellite here. I think we're looking at ionized air. Part of it is a burning satellite, but most of it is air, which emits light, because something's moving along through it with kilometers per second. What you can do with this, with views from many cameras, well, that's the whole point of the Meteor Network. You select the right observation files, calibrate the astrometry, the stars, select points along the trajectory. I had never done this. I'd seen a video where Dennis explained all this, but I had never done it myself, so this was a nice challenge. And then you get eCSV files from the SkyFit2 picking, run them through a trajectory solver, and then you have a trajectory. So this is what comes out of the Global Meteor Network. Here are the 5 stations that collaborated or that contributed to this trajectory. In gray here are their fields of view, so you can see a bit where you have overlapping fields of view. Along all the track we have overlapping fields of view, which is why you can make a track. Well, you can get the trajectory, which is X, Y, and Z. It also has a height, and that's encoded in the color here. So it starts high here above at 85 kilometers altitude and goes down to 65 kilometers altitude. What's also very nice is that the same day that this satellite re-entered, that it burned up, the TLE, the trajectory, the orbit of the satellite was confirmed again. So they measured this with radar, and well, this has all kinds of military purposes as well. People want to know what satellites are where. And it's also published that there's a site, Celestrak, and another one, Spacetrack, which publishes these TLEs. And it's very nice that we have a very recent one, only 4 hours before the re-entry, or well, at least the same day. And if you propagate that trajectory, that orbit, you get this dashed line. So this would be the line if the orbit parameters of earlier that day would still hold. We know that these orbit parameters wouldn't hold forever, because these orbit parameters tell that it would still be in orbit and it crashed somewhere here. But this tells at least that our orbit corresponds very nicely to the trajectory corresponds very nicely to the orbit. And if you can do that in 3D, so yeah, there's latitude, longitude, and altitude, height above the ground. Well, first looking at longitude versus time and latitude versus time. You see here the darker line is the orbit, which is the predicted ground track, and here's what we measured. And you see here that it fits very nicely, but it's a few seconds, or yeah, a few seconds earlier at this latitude and longitude than what the orbit predicts. And I think that's consistent with something that goes down, then it travels faster. So I think that that matches expectation. What's also nice is this plot. Well, this is the height, the altitude versus time, only of the re-entry. Well, there's some discontinuities in here, and that's because I didn't do the fitting very nicely. But you see, well, it goes down from 85 kilometers to 60 something kilometers. And if we zoom out this to fit the orbit prediction in here, well, the TLE data, that's the orbit prediction, that said that it would be at 150 kilometers altitude here. Well, it was not, it was at 70 kilometers here. So something went wrong. Well, it met a lot of air and burnt up and went down. I'm not sure how we should fit a line between this and this. I can draw something in paint. I did something like this. Or it could be that it went here and then went down and followed that line, or that one maybe. I think every one of this is an orbit around the Earth, but I'm not sure really. So I think this is very nice that you can combine the TLE, that TLE stands for 3 line elements or so. That's a bunch of parameters that you combine the known orbit with a known trajectory here and try to match it up. So I made that a to-do, and actually I won't do that. I've had enough of this by now. But but it would be nice, and that's the third to do, find formulas for the part between where the orbit was last measured and where we measured the trajectory, the re-entry. It would also, well, there's some loose ends to where I got these discontinuities. And also what would be nice, that we could do photometric calibration. I didn't do that here. So a few things that I ran into. The trajectory solver does not work on an M1. That's probably due to base map. I found a workaround to install Python in a Rosetta environment. I had some missing frames on one of the cameras. Okay, you can fix that. And there was something, well, satellites are not meteors. So what was a problem is that it re-entered at a very shallow angle of only about 5 degrees, where most meteors just enter more steeply and go faster. And some of the assumptions didn't really work. So the first time I fit a trajectory, these were the residuals up to 8 kilometers, 10 kilometers residuals. And you see a very nice parabola in here, which is not something you want to see, and you want to see residuals of hundreds of meters or meters and not kilometers. And then what Dennis suggested was to fit a trajectory per, say, 30 or 15 seconds. And when I did that, you see that the fits are nicer, but it doesn't mean that we got these discontinuities in the height. Next slide. Why did I do this, or why would this be nice? Well, my daughters were watching the Fraggles the other day, and Doc said, "What do you mean why?" I haven't even figured out how yet. Well, I can try to give an answer. It would be nice to calibrate a relation between weight and speed. So if you want to know how heavy a meteor is, I can imagine, well, you know how heavy this satellite was. So it's a kind of a calibration. You can calibrate meteors against satellites. Also, it would be nice to get an idea on the physics, well, between this orbit and the re-entry. So that's basically it. One thing, we published all the FITS files and data because I like what Ricky mentioned, the FAIR and FAIR research, findable, accessible, and I keep forgetting the other ones. We published this all as a data set on Zenodo. So if you follow this DOI link, you can find this data set with all the FITS files and the trajectory and everything. One more thing, I tried this, but this is what I did 20 minutes ago, so I'm not sure I did it right, but I tried to compare our trajectory with the one of the SMART project, and I think the SMART project has comparable cameras. I think we got a slightly different trajectory, but this might be because I got a wrong frame from the YouTube video. Of course, it would be an obvious thing to combine our measurements with those of the SMART project, but I'm not sure that this satellite re-entry is important enough to set up that collaboration. If a real big fireball meteorite would enter, we should do that. So that's it. Thank you.
Awesome. Thank you for the talk. So we're officially started our break about a minute ago, but because it's a break, we can ask any questions. So does anyone have any questions for Tamiyan? Okay, if not, then we can go our separate ways for about 4 minutes when Paul Rogermans is continuing with his talk. And if anyone wants to discuss anything these 5 minutes, please go ahead. Just unmute yourself and start a discussion about any previous talks if you'd like. That's about it. Thank you, Tamiyan.
Thank you.
Tamiyan, I have a question about this re-entry of the Starlink satellite. Was due to a big event on the sun. So do you think it will also affect meteors? If they have a big event on the sun, will this drag down, or do we take it already in account?
Oh, I thought, but I might be wrong there, that the effect of that storm was that the electronics on the satellites gets up. So it doesn't know where it is and it doesn't know the time anymore, and then it messes up. So I don't think it has something to do with the density or in the atmosphere. And because meteors don't rely on electronics to steer their way, I think it does not have an effect on meteors, but I might be wrong here.
Yeah, that's what I understood, that due to this solar storm, that the atmosphere is getting warmer and it's getting more thicker, and that's dragging down the satellites. But yeah, then my source was maybe not really reliable, but
I
understood.
I also understood the same thing, from that it was actually the atmosphere expanding due to the storm as well.
Okay, sure.
But I could be wrong.
No, but and then it should also affect the meteors, right? Yeah, but I don't think this particular Starlink was affected by the solar storm or the geomagnetic event. This was one from an earlier batch from 2 years ago or 3 years ago.
Okay, but they lost 40 or 49 satellites.
Yeah, they lost an entire batch, but this one was not one of that batch.
Ah, okay, right.
Yeah, in terms of the influence on the meteors, what would happen if the atmosphere inflates? Meteor heights would just go up. That's all it is, because then just the atmosphere density to have the same effect, it would just kind of change heights a bit, but it shouldn't be that significant.
Might be for your dynamical determinations of the mass.
Yeah, I mean, so we do use the atmosphere density model in some of our modeling, and you can actually put in like the solar activity as one of the parameters to take that into account. Okay, so now it's 18:55 UTC, and it's time for Paul Rogermans to present his talk. So Paul, go ahead.
Okay, we share my screen. Everything okay? Sound okay? Image okay?
Still a bit noisy, but we'll live. Go ahead.
Okay. What is CAMS network? In fact, the CAMS project is different from the Global Meteor Network in the sense that it's a complete professional project. The Global Meteor Network is for amateurs, by amateurs. In fact, the CAMS project is financed by NASA. and it got started in October 2010. Meanwhile, it has about 500 cameras in 16 local networks around the globe. You can see them on the map. And most of them are, in fact, professionals participating in the CAMS project. And of course, they are financed by the state. Last year, CAMS had about 470,000 orbits in a single year. That's enormous. And where do we come in as amateurs? Well, CAMS Benelux, the Netherlands and Belgium, and the Luxembourg. We got started in March 2012. Now, how to participate as amateurs in such a professional project? That's not so simple. In fact, CAMS is pretty expensive. We had to buy cameras at about an average of €600 per camera, plus each camera station has need of a dedicated personal computer for CAMS. We got no funding, so everything was paid by the amateurs themselves. And in the very beginning, the guidelines to get started were rather poor. In fact, we had to figure out a lot because CAMS was not really developed or designed to be used by an amateur community or so. And in the first years, also, we had no automatization. That meant we had really to start on the CAMS computer and put the cameras on every night, which was time consuming and a bit daunting, of course. In the beginning, CAMS had enormous amounts of false detections. My record was more than 100,000 in a single night on about 6-watt cameras. Another thing that's not very interesting for amateur community is that on the CAMS orbit data, there is a data embargo. So even the participants in the CAMS Benelux network cannot have access to their own data. And that's something difficult to sell to amateurs. And as a cherry on the cake, the most interesting results get published in journals like Icarus, which are not accessible for amateurs. So if it's all that unattractive, how did we get involved in it? Well, it's very simple. Peter Geneskes, the leading CAMS scientist, is in fact formerly a Dutch amateur astronomer. And in 2011, he came with part of the CAMS equipment to Europe to monitor the Draconid outburst. After the outburst, the CAMS equipment remained a while in the Netherlands to play with it. And before returning to the United States, Peter gave a presentation and demo about CAMS. And that interested amateurs. I was attending the meeting and the presentation, and we all said, that's something we want to have. At that time, we had no relevant alternative. And in fact, this way, CAMS Benelux got started in March 2012 with the first few cameras. About 5 years later, we had more than 100 cameras involved, and at left you see around that time all the CAMS stations we had, and at right you see how our houses got decorated with cameras, nice for the neighbors who thought we were heavily secured. Nobody paid attention that the cameras were pointed to the sky and not to the ground, by the way. Now, particular for CAMS, we use small field of view optics, about 30 on 22 degrees, which means to cover the atmosphere, you need a lot of cameras. Moreover, we don't have many clear nights. We have a lot of nights with clear spells, just clear gaps in the clouds. And the art is to put cameras at as many places as possible, pointed to the same part of the sky, hoping that at least 2 of the cameras can peer through the clouds to capture meteors and have paired meteors. And that was in fact the success of CAMS with a lot of cameras. Here you can see in the early years in 2015 how these trajectories were seen by combined cameras from different stations. And here you can see at right, in 2018, the coverage we got with all these small field of view cameras in that time. But bad luck struck on the CAMS network. The first disaster we encountered was a house fire where the CAMS participants and his family lost all their belongings. And of course also the CAMS station, Benningbroek, was destroyed by this fire. These images are from the Dutch national TV as it was national news. Another station was destroyed by smoke from an overheated computer. Also, we had a lot of problems with maintenance at the remote campsite, and different people quit for various reasons. This way, by end 2018, we ran into problems. We didn't have good coverage anymore for our camps. For signal camps, many people need these frame grabbers, and it appears they are very difficult to get. Actually, people who bought them found out they are no more compatible. So camp stations are at risk to disappear because we don't have these frame grabbers anymore. But luckily, we got the first RMS cameras in 2019 with a larger field of view, more overlap, more meteors, and we got interest from new people using only RMS cameras. If you see here the map of 2018, the red crosses are camp stations that are definitely lost. The green crosses are camp stations that are at risk to get lost because of this frame grabber problem. In the middle, you see the situation actually, and you see these yellow stations that are stations working only with RMS cameras. And the number of stations, camp stations at risk decreased because other stations also got RMS cameras. At right, you see the current coverage we have from RMS cameras. Now, what are the plans for this year? We still have 75 WATEX that are operational, but we are going to install many more RMS cameras, no more WATEX. We don't put them at random positions. We really choose strategic positions like this pair of RMS cameras with 6 millimeters in Durban. We plan 56 kilometers south of it. We will put an identical twin just to give coverage on this one. And this way we are going to give very dense coverage to the CAMS network.
2 minutes.
Building RMS cameras is also much cheaper than buying WATEX and so on. Now, the results for CAMS last year, in spite of the bad weather and all the bad luck we had, we still had almost 46,000 orbits with our CAMS Benelux network. In the same time, last year, CAMS Benelux contributed in 12,900 orbits for the global Meteor network. Now, increasing the coverage, we hope to at least triple this number of orbits we contribute to the global Meteor network. So if we didn't have had the RMS cameras, maybe we would have found another alternative, but we can say to some extent RMS and global Meteor network came to the rescue of CAMS Benelux and contributing to CAMS and to global Meteor network. Well, that's a win-win for the both of the projects. Also, CAMS at Lowell Observatory also implies and uses the RMS cameras at large scale, and I think it's in the interest of everyone. So I would say to other networks, please have a look at the RMS cameras and consider it as an alternative for older types of cameras. Thank you.
Thank you, Paul, for a great talk. Are there any questions for Paul? Okay, Tamayan, please.
So, could CAMS do something big for RMS, so for the global Meteor net? So could we put could we contribute to GMN as well?
With RMS cameras, yes, but I don't think the other way around to convert the data we obtain with the WATEX to RMS format, that hasn't been considered. In principle, it should be possible. I don't know if Peter Genescus would like it, but in principle it should be possible. After all, it are cameras, so it should be possible.
Okay.
Yeah, it'd have to be recalibrated, and every camera would have to have like an RMS plate.
I think that is the problem.
Yeah.
That is the problem. The calibration of the WATEX in cams is less advanced than
And we
RMS.
should just put a Raspberry Pi straight behind the WATEC. That would be my idea.
Yeah, maybe.
So that's how we started in the GMN before these IP cameras, and the issue was these frame grabbers, right? That is the main fundamental problem.
Yeah.
The drivers for these frame grabbers were really bad on the Pi. Okay, so Steve Welch has a question. Steve, go ahead.
How do you deal with the data embargo issues when you're
well, all the data from cams from all the networks is public online until 2016. I don't know when Peter Genescus will release a next batch of orbit data for the public, but that's where we have to wait for. I can do some analysis if I want on the CAMS Benelux orbit data, but I must be careful. I may not put it online just for everyone to use the orbit data, for instance. That's part of the deal with Peter Genescus. It's a professional project. We are allowed as amateurs to participate in it. And okay, we have to respect the rules, let's say. If they don't want the orbit data to be public, it's up to us to respect that.
Thank you. I also see that Jim Rowe has a question, but we're running over time. So Jim, if you could please save your question for the Q&A in 20 or so minutes. Next up, we have Richard with talk about the UK Mon. Richard, go ahead.
Hello, everyone. I'm trying to share, but it says you cannot start screen while others participants are
yes,
sharing.
Paul, can you please stop sharing your screen?
Okay.
There we go.
Thank you. Awesome. Let me just see. Well, hello, everyone. My name is Richard. I'm the founder of UK Meteor Network. And it's interesting because I wasn't at the last GMN meeting, but I recognized a lot of faces. And after COVID, I'm looking forward to seeing you all. I mean, even Paul back in Europe. So UK Mon, it's been a journey. It's been a journey, to say at least. I remember the times when I started in 2012, when one of my friends back in Czech Republic introduced me to the project and said, "Hey, well, do you know what? Mount this on your, on your house, point it towards France, and see what happens." And that's what I did. I'm kind of a practical guy, so we do things, and it doesn't always work, but this time it did. Persistence is the key. It has been 10 years. We are going to be celebrating 10 years anniversary, and we managed to basically do everything that we set out to. We got the Winchcombe meteorite by pure luck, of course, by just chance. And we managed to set more than 100 cameras in the UK. And that's this is not my doing. There's a lot of talented people in the UK Mon. But I'll tell you the story. As of yesterday, we have 130, I think it's 131 or 132 cameras contributing data to GMN. I think that's something like close to about 30% of all the, GMN network. But Paul mentioned that they're going to be putting a lot more cameras in Belgium. So we're going to have a competition across the channel, friendly competition. But we are adding a lot more cameras. Why? Because why not? It's better to have a lot of cameras, better coverage when, especially in the UK, the weather changes, the conditions change, houses burn, unfortunately. So the conditions are constantly changing. So it's better to have cameras which are saturating the country more than less. And at the moment, this is our current coverage. Now, these are locations, these are just locations. These are not projected onto a map with a field of view, but I don't know if Mark McIntyre or Dave Jones are doing anything in terms of realigning the cameras. But we decided not to bother too much with figuring out where to point the cameras. We just wanted to have a lot of people on board. And with the event of Winchcombe Meteorite, we had a decision to make. I thought, okay, we have something that we set out to. Maybe we played a part in there, but there is a lot of competition. And in the UK, there are 6 different cameras, but obviously we're not competing. We're mostly friends, except 1 or 2. But then the Winchcombe brought this to the public eye. So I saw that as the perfect opportunity to monetize the situation and say, okay, let's get it out there. Let's get people interested and see what happens. Because there's a lot of people that were doing meteors, and for various reasons, they stopped doing it. So pretty similar situation as Paul mentioned in Belgium, we had here in the UK. People were just sick and tired of UFO and processing everything all the time. So since 2012, since the first day I caught the meteor over the channel with Maïsuron from France, we never stopped looking. I'm going to be honest with you. I never particularly liked UFO. I liked it for what it was doing, what it was producing, but in 8 years, there weren't any significant updates. And I just started to see the cracks, that this is not the future, that something else perhaps is. So we're looking for a new kind of system for many, many years, but nothing was really aligning with our expectations. But in 2022, we decided, well, obviously earlier this year, we decided to fully embrace the RMS system. And why not? Because it ticked all the boxes. It is an open source. The hardware is much easier to use, and it wasn't easier at the beginning, of course, but it's ticking all the boxes, and all the data is publicly available. We like this kind of stuff where it is open source, the software is open source, and the data is too. So in 2022, after the Winchcombe meteorite, I sat down and I thought, okay, well, we have 2 choices here. We can become the network which fades into obscurity simply by using an older systems, or we can try to adopt something newer. And the RMS at that time, the Raspberry Pi 4 came out, and the RMS for me became mature. It became usable to use it on a large scale. And we just sort of pressed the red button, and everybody from UKMon team got on board, luckily. But why such a rapid, expansion? Automation. I can't stand. I don't know how about you, but processing UFO capture all day, I got better things to do than just sit down. And there are some things where some people expressed concerns where you could just go through the records and you can play the clips, and there's a better connection between the observer and the software and the hardware. But there are trade-offs. There were some trade-offs. Obviously, the data accuracy is much higher. I mean, there's evidence to it, and we like to do things slightly differently in the UK than anywhere else. So we thought we just want to carry on with developing the ideas such as UKMon tools, which is sending the data to GMN and also to our own server. And Mark is going to have a wonderful talk after this one, explaining the intricacies of UKMon tools.
2 minutes.
And sorry?
2 minutes left for the talk.
Oh, is it? Oh, I'm gonna have to speed up then. And it is the open source community. So what we're focusing on now is building a thriving community of amateur astronomers. That is absolutely crucial. We like to spend some time on social media, and developing new things such as UKMon Live and maybe some other things. There's a lot of talented developers in the UKMon team. So there are some of the best meteors that we got in 2021. Obviously, the left one on top is the winch cup, but this is the UFO capture. And the rest of the pictures are the RMS. And the 2022, we had already 3 interesting events across the UK. Obviously, with 130 cameras, the density becomes much bigger, so you can sort of pick and choose the data and the pictures that we can publish. So I would really like to thank every single person in the UKMon team, but I can't do that individually. But I'd like to mention a few words on the work that Mark McIntyre is doing, and the Davy Jones, who helped single-handedly basically to create the kits that we started selling to the members, and of course Chris Dackin, who was one of the first to test the RMS system at the very beginning. So thank you very much, everyone, and if you do have any questions, happy to answer.
Awesome, thank you so much. Any questions? And before that, I just want to say that RMS was also born as a project out of frustration with the previous solution. So it's it has a very similar genesis.
It was mental. I mean, we had so many cameras, and people, whenever you try to collect data, it was the biggest single problem, which we couldn't crack on our own. And then somewhere out of nowhere, out of Canada, Dennis Vida came along and said, hey, I've got this system. Why don't you try this? So I thought, okay, let's give it a shot.
The product of many people's efforts, and actually the project in maybe 2017-ish was almost dead in the water, but Mike Mazer, one friend who really saw the potential, really pushed the project forward. Yeah, okay, any questions for Richard?
They just mentioned that he set up 44 cameras.
That's pretty
I didn't mention this. By end of the year, we want to have 200 cameras.
Wow, that's pretty sweet. And what I like about it is that you guys are doing all the work, and the data is arriving on the server, and the orbits. Okay.
Well, you know what?
I have one slight worry. It sometimes happens that an English operator reports on the mailing list. I've been online for so long, and now I don't see my meteors on the map, and that's because they haven't been added to the pipeline. And that's a real worry, because then there is a station doing stuff but not contributing.
Hey, Tomo, my own camera wasn't on the list for about 6 months.
That's a pity.
They installed so many cameras so fast that I just simply couldn't keep up, but just look at the data and say like, oh yeah, that looks good, or just make the plate. It's really insane. Okay, it's time for Mark McIntyre. Mark, go ahead.
Okay, I'm just going to try and find the right screen. Hopefully it's that one.
Okay.
Can you see the right?
That's good. Yeah.
Okay, cool. Okay, so I'm going to talk a little bit, following on from Richard, about what we've done really with the live stream and with our data archive to bring bring meteor hunting to life for the general public. And I seem to have lost my camera, so hopefully, there we go. Hopefully I can turn my camera on. Okay, so Richard has already talked about UKMon's history, but as you know, we've mentioned before earlier on today, one of the problems is getting access to the data and sharing that data with people. And so we've really tried to build, over the last couple of years, we've tried to build a kind of data pipeline that gives us access to data both in real time and next day analytics that we can share with people. And I'm going to start off by talking about UKMon Live, which is our live sharing side of things. And so UKMon Live is driven by one of the UKMon tools that Richard mentioned. We've basically got a little Python program running on the Pis that is monitoring the RMS log in real time. And as it detects an event, a snapshot of that event is sent to our website, where it can be viewed by the general public. And this is what you can see if you go and look on UKMon Live. So this is a particular shot a few nights ago. Same meteor was picked up by 8 cameras, and we can see the pictures here. And we can then share that data onto social media. And this is the kind of thing that Richard primarily does. So, you know, if there's a busy meteor shower, or if it's something interesting that we see on the live stream, we can share this very quickly onto social media. And that's a great way to engage with. We've got about 18,000 followers, I think, on Twitter. And we've also got followers on Facebook. This is a great way to engage with the general public and also to show people what the cameras are doing. So that's the live stream side of it. I'm going to come back to that in a minute and back to the social media interaction in a minute. The other half of what we do is the data processing side of it. And this is very similar to what Ricky Bassam was talking about earlier. So here we're hooking in to the post-processing hook that RMS already has. And we're using that post-processing hook to upload images and video and scientific data to our cloud storage. And by the way, just for those of you maybe using IstraStream, this fits in between RMS and IstraStream, and it can coexist with IstraStream, so there's no issues there. Once the data's on our cloud storage, we're using the Western Meteor Python libraries again, which have been mentioned several times this evening as an open source Python data analytics tool. And that's generating all the matching data and lets us calculate trajectories and orbits, and you've seen some of the output of that in other talks today. And then we have a reports generator that runs after that. And the reports generator is generating a bunch of reports for our website, which I'll talk about a bit more in a second. We also generate a couple of emails that go out to camera operators. So there's a bad data alert that we send out. And that basically is looking at, has your camera gone offline? Has your camera been offline for 2 or 3 days? We'll send you an email to let you know. And has your camera generated a lot of bad data? Numbers of false detections. We've had a lot of wind here in the UK over the last few days. That's generated a lot of false detections. So the camera operators have been notified that there's too many detections to be realistic. And that gives them an opportunity to clean the data up manually if they want to, and then send in a revised FTP detect file. And finally, there's an opt-in email of matches, which we send again to our camera operators and subscribers. And I'm going to show you that email next. So this is what the email looks like. This is a very simple email. It's just a list of the detections with a bit of rough detail, the camera IDs and that kind of thing. And there's a clickable link in here, and that takes you to the output of the matching engine that I mentioned earlier. And so we've basically put some reports around the front of this. So this is the top part of the report for a particular event, the one actually we were looking at earlier on the live stream. This is showing you some what the solver tells you the magnitude is, the trajectory on the ground, some of the details about the orbit. There's a link to click if you want to download the data. Again, going back to that point about open access to the data. And below this top part, we've got all the pictures that we have of the image, the graphs of the ground track, the orbit. There's more information like the residuals and that kind of thing. And below that, the complete output of the trajectory solver, showing you all the kind of scientific data that's been generated and the uncertainties and that kind of thing that might be useful. And that kind of information, we then, going back to the social media side, we then share that back out onto our social media accounts. So if people have reported something through the IMO or through our website, or if they've seen something and they've commented it on Twitter, we can share back out the results of that trajectory solving process, show them a little bit more about what that meteoroid was, where it might have come from, and just sort of give people a bit more background information. I think that's a really useful way to help engage people with what we do. We also produce, actually my wife produces a monthly roundup video of the best sort of fireballs that we've seen on the cameras over the last month and over the last year. We're a bit behind on this, that's my fault. I haven't updated the data recently. But of course, we don't stop there. We also produce summary reports by year, by shower, by month, by station, and a fireball report as well. And we've got that going back the last couple of years. We don't go back beyond about 2020 because it was all UFO data then and we couldn't really do as much with it. But to give you an idea of what the full year report looks like, again, it's a kind of a summary of the events that we've seen. So 96 cameras contributed this year so far, 6,698 solved trajectories. Below there's a list of the brightest 10 or so. And then underneath that, there's some graphs that show you a bit of a distribution of data. So number of events by camera, number of events by shower, by day, by magnitude, that kind of thing. And an icicle diagram that shows you the lowest and highest points at which each meteor was detected. And this is all, again, information that's available on the website. And we've got similar information available by shower, and by station. And I think the station one's really useful because that lets a camera operator quickly see what his station's been doing, what it's been contributing to, that list of the 10 brightest events seen by my station in 2022. You can also look by month. And so this kind of information really helps keep our camera operators on side and engaged. So that's some things you can do. We also have a search facility. So if you've got a report from a member of the public, or if you are a member of the public, you can come to our search facility, you can plug in a date and time, and you can get a list of any matched events we have in the database and any single station events. So, for example, if you were operating a camera in Northern Europe and you thought there might be an overlap with one of the UK cameras, you could come here and see if we've got any data that might match it. And talking of data, we also have the ability to download a lot of the underlying data in CSV format. This is an example of what you can get for the quadrantids. So obviously the UFO data goes right back to 2014. The RMS data only goes back a few years, and the data format here is the UFO CSV format. So if you've got UFO orbit, you can process the data with that. And we do that by year, by month, and by shower. I'm going to come on to a couple more things. I know I'm running out of time, Dennis, so I'll be as quick as I can. We have what we call the Daily Simplified Report of Detections. And this is something that's been agreed amongst a number of networks with the help of the UK Fireball Alliance, that we're all going to produce a daily list of detections in the same format so that we can very quickly compare those detection lists. So from this page, you can download a CSV file, which is a list of the detections that we've made over the last 3 days. And finally, just wrapping up, we also have 2 APIs that we've put together recently. One lets you retrieve the match data. So going back to the orbital characteristics and everything of a match, you can get a download from our API of that data that you can use programmatically in Python or Java or whatever you want, the ECSV format, which you've probably heard mentioned earlier. And this again is a standard format that's been agreed amongst a number of networks for exchanging data. And it's essentially very similar to the FTP detect file that RMS creates, except that it's been agreed, a format's been agreed across a number of networks. And so you can use our API to pull out the details of a particular event, which you can then match up with data you might have got from another network and do your own analysis on that. So that was a real whistle-stop tour through it all. As I said, the 3 prongs of our attack are live streaming the data, putting that on social media, following up the next day with more detailed analytics and information for people, and then we're sharing the data out. We've got a number of APIs and downloadable formats. And again, going back to the thing that Ricky Bassam mentioned earlier about being open and fair, the data's all there for people who want to pull it out and play with it themselves. And hopefully that whistle-stop tour has explained this diagram a little bit better, but I appreciate I've crammed a lot of information into my 10 minutes. So thank you, Dennis.
Awesome, thank you. Great talk. Are there any questions for Mark? I see Tamayan.
I'm just the quickest to raise my hand. Oh, wait, sorry about that. Hey, Mark, this is really great, but can't we make this just global? Why? So I think this is all automated. Can't we just make this part of the base image?
Well, this is actually all running on Amazon. This is all running on servers on Amazon. So this is all server-side compute. Yeah. We've built it really for UK Mon. There's no reason why it couldn't be extended to cover other networks. And Richard and I are actually talking about whether we could do something in other parts of Europe. So yeah, I mean, this is all fully extensible. It's all open source. All the code is on my GitHub repo.
Yeah, but rather than running making an NL mon that does exactly the same thing, I think this is looking like something that could run centrally.
It could. The one thing I would caution is that this requires quite a lot of compute. There's a lot of data that's being crunched here, and my single biggest task at the moment is optimizing the compute here to minimize the operating costs. We are, as a number of people have said before, we're not funded by any central body. We don't have any, government funding or anything like that. We're totally self-funded. And so from my point of view, my biggest task is just keeping the cost of this down. But yes, absolutely, there's no reason why something like this couldn't be built for the whole global network. And I think essentially this is kind of similar to what Ricky's been talking about. Perhaps we're ahead of what Ricky's been doing, but that's simply because I started this 2 years ago and I've been plugging away for longer, I expect.
Yeah. Okay, thanks.
Awesome, amazing. Yeah, the comments Make It Global definitely would help the visibility of the network and the quality of the data interaction. But as Mark says, there are operating costs involved and also time. So as far as I understand, Mark and company did this on their own time and money. And I think to get this running, we would either need to get a funding source or maybe introduce some sort of a subscription just to make it running, as you know, with the assumption that Mark and the rest of the people would continue to volunteer their time to keep running the project. And possibly, you know, the reason why the GMN itself provides just a very kind of a very thin integration across all networks and cameras is that we first initially didn't want to force a complete solution on individual networks. But what happened now is that they grew outside of that, and that's wonderful. And then maybe we can transfer some of that knowledge to the global scale. The only question is, how do we find the funding? And, you know, would that cause some people to, you know, invest too much time in this than what they actually can? So that's something I can definitely talk during the Q&A and the rest of the workshop. So now our break is officially starting, but we can continue the discussion if you want. If you have to go away, please go away for 10 minutes. That's fine, and then we're going to officially start the Q&A.
I have to disappear for 10 minutes, but I'll come back shortly.
No problem. So any questions for Mark? Wait 10 minutes, and then we're going to continue.
I'll get some tea as well.
That's a good idea.
Okay, so it's time for our unstructured workshop slash questions and answers. So the way I envisioned this part is that it would be just a completely open discussion that can go in any direction. Any topic is welcome. Any question is fine. Hardware, software, strategic planning of the network to, scientific details, whatever you want. It can also be a type of, if you ever watch Seinfeld, like the Festivus festival, it's like the airing of grievances, just literally anything. Anything is possible. So perhaps we can start with some topics that we already have jotted down for discussion. And the first thing I would like to talk about is using a flat glass in front of your lens versus a dome. So why am I always advocating for using a flat glass instead of a dome in front of your camera? So just want to show you two things. So what I have here are two types of data sets in this calibration examples folder. I have a data set that does not have any, it has a flat glass in front, and I have another one that is 6 cameras under a dome. So what we're going to do is we're just going to load the flat glass data set into RMS, into SkyFit, and I already did the calibration. So we're just going to very quickly load the state file just to see what I did there. So here we have SkyFit. You can see it's actually amazing data, very dark skies, lots of stars. You can see the Milky Way, and I picked a lot of stars for calibration. So what I can do with this is I can press the fit parameters button in SkyFit, and this is going to fit our astrometric plate. So if I look at the graph of errors on the image, you can see that the errors are random around the 0 line, and the total, the error standard deviation, so that's basically kind of a mean error, is on the order, is less than 1 arc minute. It's about 0.8 arc minutes. So that's kind of nice and precise. So this is how we want all our data to be. This is kind of a level of precision that we want to achieve. However, if we look at the data that has not a flat glass, but a dome in front, and then you can see that the data actually still look pretty good. Still lots of stars, and I picked a lot of stars, and there's one nice big fireball here. That's not important. If we were to look at the astrometry calibration here, you can see that does not look that nice. There's some trends, there's some issues, the error is much higher, and if I actually look at the number here, we're talking about 3.5 arc minutes versus maybe 0.8. So a dome introduces a lot of distortions in the image that simply the calibration method that we're currently using cannot deal with. I think we can probably upgrade it to be able to deal with this. But then there's another issue. The issue is that the dome might warp over time with changes in temperature, et cetera, while, for example, if you have a glass in front, glass is much more thermally stable than plastic. And in the long term, the calibration quality can be much better. So why am I even discussing this? Well, if we're interested in fireballs, and if we want to make sure that we have very accurate trajectories, the difference between 0.8 arc minutes and 3.5 can mean the difference in the precision of the end point of the fireball can be increased from maybe 50 meters to hundreds of meters. So it actually makes a big difference if you were to go there and actually search for the meteorite, what kind of accuracy you can achieve at a certain point. So that's basically all. So initially, we in the GMN were deploying cameras with domes. However, we recently realized that we shouldn't be doing this and should basically switch everything to like a flat glass configuration. And also, if you want to achieve all sky coverage, so let's say from one station you want to have like 6 or more cameras, well, what you should really do is to have like a tiny little flat glass in front of each camera and try to construct some sort of a dome, maybe like 3D print some sort of a system. It's something we learned very recently and we just want to share with the world. Okay, the next topic of discussion that we have on the list is that currently we seem to have, well, the bottleneck of the network is that, as discussed before, there are some cameras sending the data, but they're not added to the pipeline. So what we should really work out is maybe a core team of people who know how to generate good plates in SkyFit. And we should probably have a separate internal mailing list. So when a new camera comes in, that we can basically say, there's a new camera that's joining the network. This is the operator, this is the code, and the next person available to look at the data and calibrate the data should correspond with the camera operator. Because the way it works right now is that I hear that something's arrived, but maybe at that point I'm so busy that it might take days or even weeks for me to realize that. And also another point is that if you don't tell me that the camera is sending the data, I will probably not check unless I notice that one camera is uploading a ridiculous amount of data and something's wrong with it.
You can change that. That's something that can be automated, right? I think I could even automate that, because if you have access to the directory, so that's just an automatic script.
Yeah, so what we should ideally have is basically, IstraStream. Not all cameras are on IstraStream. It's a step that's done separately by the camera operator, and it's really done by the camera operator. What we could do is on the GMN website, create a page, like an astrometry status page, where for every camera, we could basically go in and say, this is a list of cameras that are added to the pipeline. These are the calibration plates. So we can very quickly check for all cameras, their status. But this is probably a part of larger upgrades that Ricky might do at some point. But I'm also open for anyone's contributions.
I think the idea of having a sort of small core team that help get plate powers sorted out would be really good. I mean, I've made quite a lot of plate powers for folk in the UK, and actually a few for people overseas as well. And it's something that once you get the hang of it, doesn't take too long. And I think that would certainly help a lot. And if that's the best way to get the pipeline updated quicker, then yeah, I'd definitely be on for helping out there if I can.
That's great. Yeah, I might. Yeah, go ahead.
Sorry, I'm new to doing the plate power. I only just had to do it, and frankly, it surprised me I had to do it. Methods around these days, and it's used for my telescope alignment. Pixel Insight uses one that's distortion in it as well, and they're all automatic and seem to do extremely good jobs. I'm just puzzled that it required this amount of human intervention, which actually seemed quite tricky. Am I just missing something?
You'd be surprised how hard it is.
I know it's not trivial, but there seems to be so many that do an extremely good job. I'm surprised that this is it really, say, an order of magnitude more difficult than all the other ones around? I mean, the Pix Insight seems to do it to a tiny fraction of an arc second almost every time.
So telescope images are much simpler to calibrate than wide.
Well, these do have distortion, though. They do have quite a bit of distortion in them because it can take large field of view
can't
as
even
well.
be compared. It's another level of this. It's just the amount.
It is that order of
complexity.
magnitude.
Yeah. Because
of the field of view, right?
Yeah, but I do it with wide angle views as well. So I can stick a normal camera lens on. It's got a 30 or 40 degree field of view, and it still does it.
Yeah, have you tried to compare the astrometry?
No, that was my next thought. Yeah, I thought I probably would, and so I could have some evidence, but it was just my initial reaction was a surprise.
Please do so, and then you will see why we are pushing this solution we are pushing right now.
Yeah,
because the difference is really, really important.
Yeah, and it's not just that. The manual intervention can also help to distinguish which stars to really take for the calibration, and something that automated methods might have an issue. Now, hopefully, I dream of a day where I won't have to do this anymore. It would be amazing. We just give it the image, go to the location, you do everything automatically, find the best solution. But the complexity at this point is such that it is best if a human operator can spend 5 to 10 minutes per camera, making sure that the plate is fine, and then that's it. And then there's also, the way things happened in the past, there was a human in the loop every day looking at the data and reducing things. But now we reduced that to literally just almost one check per camera deployment in terms of data quality, and then everything is automated from that point. So it's good to have at least some human intervention to understand what's going on, and to someone with at least a little bit of experience to look at the data and say like, oh, no, that's not good, something needs to be changed, something needs to be fixed, just to guarantee such a high level of data quality. Any other comments? Okay, so the next item that I have on the list is the Tau Herculid outburst in May. So that's something that we should kind of all be putting in our calendars. The Tau Herculids are a meteor shower that is usually has a very low activity, but every once in a while it has quite a significant outbursts. And this year it's gonna happen May 31st. And we might see a really, really big outburst because the filament, the meteors that were released from the comet were released very recently in 1995. And on astronomical timescales, that's very, very recent. So we might or might not see a big outburst. So either it's going to basically be nothing or a huge outburst. Something to put on your calendars for May 31st this year. Just nothing special that needs to be done. Just make sure your cameras are running. Okay, so the next item that we already started discussing is a UKMON style web page or some sort of a status website for other cameras. And now that's the discussion that we should, have with Mark and everyone from the UKMON in terms of they already have a really good solution. And now the question is, can it be expanded for other networks, and how would we do that? What kind of resources do you need? What kind of maybe financial support, or does it take just too much of your time and you're not going to do it? What are your thoughts about it?
Maybe if I start by just
Go ahead.
I've been working on the UKMON solution for a couple of years now, probably putting in 2 to 3 hours almost every night on it. So it's been kind of almost a full-time job for me. So there's a lot of work. And I think I would probably break it into two halves, though. I would say the one half is the data processing pipeline, which I think actually GMN already has. And the second part is, building kind of a reporting website interaction process from it. And my thought on that is it's quite a subjective thing. Each network might have its own ideas of how it wants to present that data. It certainly could be done, but as you said earlier, Dennis, it is a lot of work. There's I said I've probably put in hundreds of hours of effort into this, and my wife tells me I spend too much time on it. So
fair enough. Yeah.
If I can add to that something, we've had some questions from, I think it was Belgium or some other European countries where people say, oh, we want to join UKMON because of the access to archive, because of the reporting, because of various different reasons. And I had a brief chat with Mark about this, and we thought it's a good idea in principle that each geographical area, let's say country, should have their own version of this, whatever this is.
Isn't that a bit of a UK-centric view? Because as you may know, the rest of Europe is kind of countries that are close to each other. There's no channel that separates them.
I am from Europe.
Yes,
myself.
I know. Yeah, but there's not a big channel, so there's lots of overlap of meteors.
I didn't get to this point yet. What I'm saying is that each different country has their own definition of what it should be doing. So, for example, I know that there's a big difference between, let's say, how Polish want to do their network or how the Czechs want to do their network. The Czechs like to fiddle with things. And there may not be the case for each country, but in general, yes, absolutely, they should be sharing data. That's not the problem. But it's just what Mark has done, he took the initial idea that Peter Campbell-Barnes worked on in R, and he took that and expanded it with the possibilities of RMS or Global Meteor Network. But I'm saying this is our interpretation of what we thought it should be. Access to the archive and sharing the data. But that may not sit very well with, for example, people from Czech Republic or Slovakia. They might say, well, we're not quite ready to share that data yet. Maybe or maybe not, but each country has their own definition of what it should be doing.
I don't think there are enough programmers or enough marks around to cater for all possible requirements.
Yeah,
so
Mark is unique and he's ours.
but so say some of Mark's time is operational time, so that happens on a per meteor basis or per state that scales with the number of stations. But lots of Mark's work, I could imagine, is setting this all up, or making the instance run, and making the instance run does not scale with the number of meteors or number of stations.
I would, if I may, just pass this question to Mark, because our idea of making this scalable is, in the cloud and the power of Amazon. The only problem is the cost.
Well, if it's a matter of cost, that's something that's very easy to discuss, right? Tell us how much money you need, and then we can find a way to make that work.
I would leave this to Mark to say whether, how he feels about saying, yes, my script is ready, have a go.
I mean, I guess what I would say is that all of the code is open source. It's all on GitHub, so people could have a look at it. I guess the thing is that it's grown up as we've felt that there were things that we wanted to do or to show, and so it's kind of unstructured at the moment. It would need a lot of work to tidy it up. But I think also it does some things that are probably quite specific to the people that we're working with. I mean, and I think if you want to do this on a global basis, you would need to try and work out what's the minimum useful piece of product that you could deliver. I'm as well as being an astrophysicist and a data scientist, my actual job is a computer programmer. So, from the point of view of how I would suggest this could be approached, you would need to figure out what is it that globally we would all like to see. And Dennis has mentioned one thing already, some kind of status page almost that shows you which cameras have got good quality astrometry. That would be really useful. We as a status page on our website, we've just got like the all-night stack and the sort of sky map of all the detections on each camera. And that's quite a useful way to just know if cameras are still producing useful data. But something like that might be a good starting point. The other difficulty is that, and this is where the geographic thing comes in. As a UK-based organization, we only have cameras in one time zone. We only have to deal with data that arrives at one time of day. so we can process stuff in a particular fashion. If you're handling a global data set, it's going to be arriving 24 hours a day. That gives you a whole new set of technical problems in terms of data processing, keeping your systems up to date. I know there's been times when there's been so much data coming into GMN that the systems have kind of been lagging by sometimes days, and that's not a criticism of anybody. It's just how it is when you've got a lot of data. And obviously the more cameras we add, the more data there is. I've actually had to put some throttling in on some of the data feeds so that we now reject cameras that generate more than 500 detections a night, simply because that's almost certainly junk. But otherwise it overwhelms our data pipeline. So there's things like that you would need to think about. But I do think the way to approach this would be to find what's the minimum thing that would be useful for everybody, and then see how you can put that together. It's kind of where we started with UKMon, it's just what was the smallest thing that we thought would be handy.
The report.
I have a couple thoughts from our perspective, and I'll be presenting on the New Mexico meteor array in the second session. But if you stop and think about generalizing this, the U.S. has several time zones, as you pointed out. Some of our states are as large as some of the European countries. So where would this go? I mean, would we have one of these for each state in the U.S. and each province in Canada? It would just become disorganized, essentially. I think the only way forward
in terms of time zones, you get. Yeah.
Sorry, go ahead.
Sorry, you could have one for the Americas. Then you would at least have a break in when you can process.
Yes, that's true. That's absolutely true. But we're going to include all of Mexico, U.S., Canada, and then we've got South America, which is really similar time zones. So basically, we have a huge geographic area that would be all acting at pretty much the same period of time, both northern and southern hemispheres. If you're doing time slices across, I mean, it's interesting to consider. We've developed something here that's homegrown because it developed the same time InstaStream was expanding and the same time UKMon was expanding. So we need to start pulling these regional differences into a little bit more of a global integrated approach. So money is, of course, a major concern. I understand that, but as a long-term goal, I think that's where we should be headed.
In terms of what the GMN provides right now, it's a very, very base functionality, and that is what just I can offer and maintain. And it's just meteor orbits within 24 hours on the website, and that's soon going to change with the addition of the flux. So that's kind of the base functionality in terms of what we can justify in terms of our science goals, right? And I can completely understand concerns that Richard has, that different countries might consider doing things differently. So for example, we have some participants in the network where they've basically started installing GMN cameras in their local network and just slap the name of their national network on it and say, this is ours. They don't really participate much outside of it. And that's perfectly fine. I think, this is where the network is great. It was able to reach people who are not that open to collaboration, and that's great as long as the data is being used in some real scientific way. Now, in terms of some operational enhancement of the network, I think we have several different things that we can improve. So first of all, and that is noticing fireballs. So right now we have a really big almost downside of how things work is that the cameras, the systems were designed for fainter meteors, and the fireball functionality was almost kind of slapped on top of it. So it just kind of works in a certain way. So some fireballs might get missed and happen before, or people noticed a week after. We have to improve that in some way, find some sort of a way improvement, maybe improve the fireball detector. So remember when Tamoyan showed the detections on the satellite trail and just a couple of little frames? It's true, like that code hasn't been touched since 2015 at all. I wrote it in a couple of days in June in 2015. That's it. It's just unchanged since then. So that needs to be looked into and improved, because I understand, and fireballs are a big focus of the network. And then, here with fireballs, things can become a bit more complicated because there's always a lot of controversy when meteorites are involved, because you might get meteorite hunters and there might be some issues. So that's why, at least in that part, as you might have noticed, we do faint meteors, we do orbits of faint meteors, everything's public. But with fireballs, I don't really touch that a lot because, like, if people want to do it locally, then I'm going to tell them how to do it. But if they have some other ideas, I'm not going to get involved. I'm just happy that they're sending data, right? So then I kind of feel that we will never be able to overcome the kind of, the full integration for fireballs unless you want to do it on a kind of controlled national way or within a network, right? Yeah, these are my thoughts. And again, just to the camera quality. So people said, oh, I want to get an email if my camera is not working. That's a definite improvement that we can do. Sorry, other ideas. Damir, you want to say something?
Yeah, regarding fireballs, there's lots that can be done, and we don't have to rely exclusively on summary images from the whole night and stuff like that. Perhaps we can get some use of those light curve files we have, perhaps go through them and find common peaks. Then again, there may be issues with lightning if some thunderstorm strikes nearby. Then we have lots of positive detections on that. But yes, fireballs remain to be things we have to find a way not to miss any of them. That's something that we should work on. And one of possibilities is to check out if those light curves we can recreate out from data available after the night is done, or perhaps even earlier. I think FS files are being stored immediately after the detection has been done on FF, or even earlier.
They're done in real time.
In real time.
Just for context, we have a separate file. You heard about FF files, you heard about maybe FR files, but the FS files are those that have like a sum of all pixel intensities on the image are stored in there. And the reason why we do this is because all other types of compression are gonna degrade the image quality, and that information is gonna get lost. So if you basically look at like the background and then suddenly the value in the FS file peaks, it means there was a very bright event that occurred at that time. So that's something that can be used for some sort of a simple fireball detection, fireball correlation.
And one of the things we can do is actually go through those FS files we have for known fireballs and check out how we can use this in order to have some fireball alert the very next morning or the very next day. Oh, actually, it should be the very next morning all data arrive. So we can jump in and save those FF files immediately.
Yeah, that, and also we should not forget about making sure that the data is available for viewing publicly, and then people could say, oh, there's a fireball, did you check that out? Because we still want people to have eyes on the data. That is like, we might get a really like weird fireball. I don't know if you guys seen maybe a week or so ago, I posted this multiple fragmentation fireball. That thing would have probably been missed if, by some sort of automated way. So we really want people to look at the data and say, wow, this is really weird. Like, what's going on here?
We have that in the UK, yeah.
Then you can have cases where the fireball happens in the twilights, and then you will not see it just like that, because on stacked image it will be very, very, very pale. So I almost missed a couple of such cases, but you train your eyes when you're looking at those images, and then you see that something's wrong, that this bulb you are seeing on a stacked image, you don't see it just like that on the summary image. And then you go through details, then you find it somewhere in late evening twilights, there is a bulb. Then when you go check it on other cameras, you find it as well, and you find that there are actually existing FR files with the image of the fireball. That's something that can slip through if you're not carefully looking at those images.
Yeah, just kind of finding a way for the general public can look at the data in a simple way. That's basically what IstraStream is trying to provide, some base functionality like that. And the next step is, how do we get people to actually look at that data, to be really interested? So, I mean, there are a couple of stories that really, would, point out the value of that approach, and that is that the NASA Fireball cameras have an efficiency of over 99.9%. It's because their boss's boss and their boss is really interested in fireballs and looks at the website every single day. If one camera goes down, he calls them directly and tells them, yo, something's up, go fix it. So the question is, how do we find that type of person or someone who's interested to really look at all data of the Meteor Network, just to, someone has an eye. So Keith, go ahead.
Yeah, like I'm more like just a user of the. I point my camera at the sky, and I'm not really analyzing the data. Well, that's behind my capabilities. So, but I thought the discussion was started like, how can we get people involved to look more better at how the camera is working and blah blah blah, etc. And I see two projects which can help very good. Like the UK Mon started with publishing more pictures and etc. More, let's say, to understand for a normal user like me. And Tamayan did the same with the Meteor map. So I think that helps also a lot. Everybody was really glad to have a nice overview what's happening and etc. So I think such simple tools can help to get people, let's say, close to the network and keep looking at what's going on. So maybe we cannot really copy maybe what Mark has done for UK Mon to globally. I understand that, but for example, if we use, it's just an idea, just to use the Meteor map from Tamayan, and we can hook the MP4 files which you have already to the same map, then everybody, something simple, that just to get the people, I would say just keep it simple to start with, and then for data analyzing, that's really for the pros to go. They will find the data anyway, but to get the normal users on the line, I think we have to give them some simple stuff that they understand when they look at it.
So in terms of what's already offered by, for example, like the IstraStream weblog, what kind of improvements do people see that can be done to that website that are maybe not very complex, but in terms of just maybe a simple improvement to make that website more usable to the users? I see some hands up. Maybe we can address that first. So Chuck Pullen had his hand up for a while. So Chuck, go ahead.
Hi there. I'm lucky, it sounds, in that I only have one camera, but that's building. I have another one ready to deploy. I look at the captured images each night, or I try to, for anything that got missed. And, that's the Mark I eyeball and analog analysis, but it does work. And I've caught a couple of fireballs that way, as well as some other weird stuff. I realized if you were running a network of 100 cameras, you couldn't do that. Or if you could, you'd be institutionalized. But I mean, is there another way to even automate the sequence of images that come, so you could sort of scan it a lot quicker? I mean, the carpal tunnel of clicking advance on each image is a possibility. Thank you.
I believe that there are tools developed by Mark, if I'm not mistaken, that allow something like that. That would just very kind of quickly show the images in a quick succession, and then you're able to stop it. I don't know if Mark is here or not.
He's not, but I can answer that.
Yeah, sorry.
I could put that on the listserv too and ask.
Yeah, Mark had to pop out, but I can answer that.
Oh, okay. Okay, yeah, go ahead, Richard.
It kind of boils to whatever the purpose of this reporting is going to be. As Keith mentioned, he likes to have a look at it as the normal user, where what was it, Mark? Gentleman who spoke earlier, he mentioned that he likes to go through it. This is the UFO versus the new system. I think that this is all about who has time for it. I don't. When you have 7 cameras, I don't have 7 cameras, but if you do have 7 cameras, you're not going to have time to go through all 7 cameras. And it doesn't matter how much you automate it. But what you can do is publish that information onto some kind of an organized filter, you came on live like thing, where people who do have time, they can go through it and they can say, hey, this is interesting, because otherwise I would miss that. You know what I mean? So if you push it out there for the public, those who have time, they can do that for you.
Yeah, so now the question is, how do we reach that element of the public and create a website that's accessible? Yeah, accessible to everyone.
Easy.
Well, but that's exactly like the Zooniverse project. Yeah. I mean, this was done for galaxy classification. That there were thousands and thousands of images that needed classifying, and they just put it out for the Zooniverse for humans to look at. And, you know, there's enough of them keen enough to spend a bit of time to do it, to get through that data set, which any other way would have been impossible. And this seems a very similar problem. So it needs a similar solution, maybe.
In a sense, I don't think we're really missing that many things already, except maybe some fireballs that get missed from certain stations. However, it would be good to make all data in some format available to the general public, as long as we kind of scrub the location information. But yeah, I would love to hear more about this. So Marco wanted to say something. Marco, go ahead.
Yeah, I mean, in general, it's the same as the Stardust mission, if I'm not mistaken. Not mission, the Stardust website for analyzing, for searching for micrometeorites in aerogel. I don't know if anybody's familiar with that. But basically, they collect these micrometeorites, and you can participate in searching online. You basically go through a tutorial that teaches you how to recognize what is and what isn't a real detection, and you have basically the option that a certain amount of users has to verify a sample as it being a micrometeorite, and then you have it sorted out. So I'm not sure if I remember correctly how exactly they started the whole thing regarding to the public outreach, but maybe it would be good to have something simple to reward people for contributing to that. I had basically an idea before which wasn't very scientific, but maybe would be useful now. Then Dennis is laughing because he probably knows what I'm talking about. But do you want me to mention it, or do you think it's not appropriate? You be the judge.
Maybe we can discuss this later on.
Okay.
But it's an interesting idea, definitely. Yeah. So Case has a comment. Go ahead.
Yeah, that is like a simple operator. Istra Stream, how do you spell it? Istra Stream. I look at it daily to see how the cameras are working, and it gives me a very quick, understandable overview if everything is all right or not, or whatever. So, yeah, it's working. And I think just maybe that one together with the idea of UKMON and the map of Tamayan somewhere in the middle for simple operators, useful, understandable information.
Okay, that's really good. Yeah, it's good to hear that it's satisfying some based way of looking at the data. So possibly some minor improvements and tweaks to ISTRStream would probably satisfy most. So does anyone have any experience with ISTRStream or think that it might be upgraded in some way? Because we actually have, I think, people here from ISTRStream that are listening in, and they might make those improvements if suggestions are made.
Okay. The only improvement I can imagine is the mobile version of ISTRStream is, at least on my iPhone, not working really correctly. You have to tap a picture and then it reloads, and then I can scroll down to see the images of the night. But that's all. On a normal computer machine, is working perfectly. So yeah, and I'm not sure how they are funded actually, but I think they do it also for free or something like that.
Yeah, they have a server in Germany they recently upgraded to, and they're just funding it from the money they get when they sell cameras, as far as I understand. Yeah.
Okay.
Paul, go ahead.
Yeah, one of the improvements that was made a few months ago on the iStream webpage, that there are these colors before each camera, indicating that the camera calibrated and everything is okay. So what I do for all the Belgian cameras, in principle every day, is to check if the capture ran from the evening till the morning. As that sometimes fails, and that indicates the camera is in trouble. And otherwise, I also look at the calibration to see if the astrometry and things are still okay. Because the danger is with automated systems that once it's running fine, you lose it out of the eye, and the day it doesn't function anymore, it may take days or weeks before you come after it. So,
exactly so, Paul. Exactly so, Paul. And that's why we added those stars in colors besides the flag, which says which is the status of the camera. So green square or red square is saying upload has been done or hasn't been done, while stars in colors say, okay, if it's green, then calibration is okay. If it's red, then calibration is not okay. So in case you have the night uploaded to the server, the score will be green. In case astrometry went well, the star will be green as well. But if astrometry fails, then the star will be red. So you see at glance if everything's fine. If everything's green, perfect. If something is red, something is not okay.
And orange?
Orange means you haven't had updated your system for a while.
That's strange. Normally should do that automatically. I should check that.
So just for context, if there are people who are wondering what we're talking about, this is the ISTRStream website, and these are the stars that people are talking about and the status. So obviously some cameras, for example, if they upload it in time, if the calibration is fine, everything's green. So orange if we're still waiting for the camera to upload, and red if the camera hasn't uploaded in a long time and the calibration is bad, right? And also the calibration star is also going to be red if there are no detections, but you can very easily check that by actually looking at the stack of detections. Okay, so there's a hand from Derek Poulton. Derek is from Australia, so welcome, Derek. Please go ahead.
Yep. Good morning, Dennis. Yeah, just to comment on ISTRStream, we've got 3 cameras here, and they're all on ISTRStream. I tend to look at my detections in the morning, but if I find something interesting, I'll go and look at the other two cameras, and you get a different view of it. So, and also I don't know who runs the Melbourne camera, but I know it's been down for a long while. So it's good to sort of get an overview. We're going to have many more cameras shortly here in Victoria. So so InstaStream is going to be fantastic for us. So yes, it's a great tool, and Dama's been very, very helpful getting those up.
Awesome. Thank you for the comments. Okay, any more comments about any tools that we can make or use to make our lives easier in terms of reviewing the data? Richard, go ahead.
Speaking from my own perspective, is I am quite busy, which means that I don't always have enough of time to check up on camera. So personally, from a simple user as I am, I would like to know whether my data, my camera is sending good data or bad data. I know that Mark is already working on this, but it is something that you need to tell the operator to say, hey, you know, maybe your camera moved in the wind that we just had in the UK. I wouldn't know. So the camera would stop working and I wouldn't even check it. Mm-hmm. So that's just notification system.
Yeah, so basically the suggestion is that InstaStream should upgrade to include like sending emails, and then you could say, well, this is my email address. If something happens, please send me an email so I know.
Yeah, something like this. It's just to notify the user that either the mask isn't aligned or the data that is coming out is problematic. Maybe there's some kind of corruption, you know, whatever the problem is, notify the user.
Okay, I got it. So Richard, UK Mon doesn't have this option available at this moment.
Mark is working on it. We're working on it.
It's easy to do it. It's a piece of cake.
No, it's not.
Yeah, because we adopted it a month or so ago, and it should be doable for Mark in a couple of minutes.
Really?
Really?
Right. Okay. Well, hey, I'm just saying.
Okay.
That...
If you have any doubt, ask who's the one who said a couple of minutes ago that it works perfectly.
Okay, we're sending the email to the user if there's more than 700 events or something.
No.
But that's pretty much it. That's all UKMon does.
No. You can. What you can do is check out how astrometry went.
Okay. We're not doing that now.
It's so easy because in case astrometry fails, there will be no file on photometry.
Okay.
So
well,
there will
the graph. Thank you.
The graph which represents the photometry results will be missing. So if there is no photometry JPEG, something's wrong with your astrometry, and you can ask, you can. And if Mark is here, he would be already typing the solution. So be running in a couple of minutes.
Okay, thank you. But it can go further than that, yeah.
But that's what you need to let the person know that, like on InstaStream, you can see plenty of stars and astrometry fails. So either camera moves, something got wrong with plate par or stuff like that. But in any case, you have to act.
But you have to have the InstaStream.
You don't have to have, because you now know how to do it.
Right, gotcha. Okay, I understand.
Just check out for that photometry JPEG. If it's missing, then something's wrong. Go look there.
Okay.
Richard, may I ask you something?
Of course.
But I understand you look quite often at your mail, so then you can also look at the website of InstaStream to see if your cameras are working.
My cameras are not running InstaStream.
No, but I was only wondering. So what's the difference for, let's say, simple users as I am as well? Either I have to look, I receive an email to get the note to get notified that my camera is off, or I have to check a website. Yeah, for me it's the same effort to do.
Yeah.
So,
okay.
Right? No.
Right. Well, right up till today, I didn't know there was InstaStream. Okay. So there was, UKMON started developing their own things because we wanted to have access to the data and play with it. And this notification came out of it, and you just guys told me that there is InstaStream, but as my understanding is, you can have either InstaStream or UKMON tools. I don't know if you can have both, maybe?
Yeah, why not?
Yeah,
I think Mark mentioned in his talk that you can.
All right, well,
it's just it goes in between the normal pipeline and the Istra upload. Well,
So
I have
there you have it.
one question, maybe slightly technical. There used to be a problem with the Istra stream and the reboot. Someone who gave the reboot command. Has that been solved in the past year?
So the InstaStream script currently is still going to reboot the Pi after it finishes. There is a functionality, right? So the issue is we can probably change this in some way, but the issue is that it's going to reboot the Pi while probably another script is running. So it'd be probably wise to run one set of tools and then InstaStream at the end if you have any other scripts.
Okay, yeah.
Right.
I think I do that as well for my custom script. Yeah. Okay. Thank you, sir.
Okay. It seems so. So Pete Ashman, go ahead.
Yeah, I'm considering this problem right now because with our external script, which I'll touch on in the later presentation section, I'll touch on a lot of this from a local perspective, but our external script could be fairly easily modified such that when it was done, it then called the InstaStream script. And that way, we would actually stop doing some things with our script and let the InstaStream script do it. But there is this problem of concurrency of how to sort this out in such a way that all the objectives are met when we can only run one external script.
You can run as many as you want, because the way it works is that you just make another script that runs separate scripts.
That's right.
It just does things like that.
Yeah, my custom script wants to make a time lapse, for example, as any script would want to do, and upload that time lapse. But InstaStream is going to generate the same time lapse, so that's a bit of a waste of.
That's
compute.
exactly what I'm talking about. Precisely, we make our own time lapse, we make our own captured stack, and so we would basically have to find a way to defer that action to InstaStream.
Or have InstaStream use your time lapse. It would be nice to have, like, you can make that a setup thing that you can just tick the boxes. I want to make a time lapse. I want to do this, upload to UKMON, upload to GMN, upload to InstaStream. Just tick the boxes, and that wouldn't be very hard. It just takes some programming.
So one thing that can be done probably very easily to modify the InstaStream script and basically tell it, after you finish running, run this other script. And then after that script finishes, it would be like an external script for InstaStream. So after it's done, it generates all the stuff. You can take that data, do whatever you want, and then after your script finishes, InstaStream is going to reboot.
Well, actually, the whole solution would be because you can already. That's what my script calls InstaStream once it's done, and at the end of it, it could run another script. Except InstaStream wants to reboot.
Yeah.
So that's where everything fails.
We can modify the script, so we can say like reboot or not. There's like a little flag. I think that could probably very easily be done.
Yeah.
It's already taken a lot of arguments, right?
Yeah.
Okay, I think we might have exhausted this topic, and we should probably move on. What I would like to do now is just answer some questions that people have sent in. So I'm gonna just quickly share my screen. And actually, Case asked a question. I was wondering how meteorite streams affect the operation of spacecraft like satellites and manned stations like the ISS or Tiangong. Will or can they avoid a meteoroid stream? Is and how is GMN data useful for spacecraft for collision avoidance? So actually put this, your questions in this document, and I shared it far and wide. And Bill Cook, who is running the NASA Meteor Environment Office, read these questions and answered these questions himself. So I put these questions here in this document. So Bill answers, meteor storms can force spacecraft to take mitigation measures. Shuttle launch has been delayed, Discovery 1993 Perseus. Spacecraft have shut down high voltage supplies like Chandra, reoriented so their hard side faces the meteor radiant like the Hubble, and rephase orbits to use planets as a shield. So Mars orbiters with Siding Spring Comet. But in general, meteor showers only pose a few % of risk caused by the ever-present sporadic meteor background. So nothing is done. Meteor storms can be a different story. As far as collision avoidance, only detection systems capable of the high precision tracking of meteoroids in space can help, but no such system exists. We simply identify periods of higher risk and assign a hit probability for a given vehicle, a spacecraft. GMN data is useful for refining forecasts that identify the higher risk periods and for providing data that improve the risk numbers. So what that basically means is that we have people running very complex models of meteoroid streams, and they make predictions of when meteor storms are going to happen. But to constrain these models, we need previous observations. So currently they use the IMO visual data, they use the radar data, any data that's available. However, that type of data sets to have some drawbacks because some of them are non-instrumental and the radar observes very small meteors, and that's where the GMN comes in. Another question, if we see on Earth a meteor shower, will the crew of a manned spacecraft also see the meteor shower? Bill says, yes, if it's a major meteor shower, Perseids and Geminids have been seen imaged many times from orbit. The difference is that astronauts look down rather up. Surprise, surprise. Okay, another question. Are they at bigger risk during such a stream passage? And Bill says, yes, but usually no more than a few %. Meteor shower activity forecasts are folded into the risk assessment performed before ISS astronauts go on spacewalks. And the last one, can we put an RMS camera on the ISS? And Bill says, possible if you have big bucks and a ride. Takes about $5 to $10 million to certify a piece of hardware to go on the ISS. Can't just load it onto a cargo container and send it up. There's a lot of effort, a few years to work out the logistics, location, data connection and transmission, rate times, maintenance, blah, blah, blah. Will you give more information than ground-based systems? I doubt it. So there's actually a really funny story that some people from Japan were trying to send a meteor camera up to the ISS for several years. And every time the camera was riding on the rocket exploded. And I think it's only for third or fourth try that they were actually able to launch the camera. And I did see their presentation, I think in 2019 about like their results. And it was an incredibly frustrating presentation because as Bill says, there isn't really much kind of scientific use of the cameras or an ISS. The problem is like how to calibrate it. When we're on the ground, we're looking up, we calibrate on stars. But when you're on ISS, what are you going to calibrate on cities, on like, I don't know. It's really hard just to figure out what. However, there's one scientific case why to put a camera on the ISS or in space, and that is to record spectra of meteors. So just to figure out their elemental compositions from the light. And the reason why that's much better to do in space and not from the ground is because of the ozone layer filters out ultraviolet light. So we can't really see any ultraviolet light on the ground. And because of that, we don't have skin cancer, right? Which is great. However, all spectral lines of carbon compounds are in the ultraviolet. So if you want to figure out that if, for example, organic material like building blocks of life are raining down every day from the sky from meteors, what you really have to do is you have to put an ultraviolet spectrometer in orbit and record meteors. No one has ever done that before. There's only just been one recording of like an UV spectra of a meteor, and that's not, it's very shaky. So we don't really know if, you know, key components of life are just raining down on Earth every day, and that's just one case to do it. And the Japanese team, they actually showed, oh, our window is actually sensitive in the ultraviolet, like it's actually, everything's fine. And then I asked them, so is like the camera like sensitive, like the camera itself sensitive into ultraviolet? They said, no, we didn't even think about it. It was a very frustrating presentation. So that's one big thing that can be done if you have $10 million, right? Okay, and Patrick Franks, I think he had to leave. He had some questions, but it would be good to answer them as well. So he had a question of how the detection discriminates between planes and meteors. So, well, it really doesn't in most cases. And the problem with planes is that they can really look like fireballs, and the fireball detector often picks them up. However, it might be possible with some more advanced processing to figure out what's a plane and what's a meteor, but that doesn't seem to really cause many issues in terms of computing the orbits. And also, he asked use of more recent cameras. So we're always on the lookout for new technology and how to incorporate it. However, we still haven't found any better cameras that are as cheap. We have the, you know, the IMX-291s, the IMX-307s, and
yeah, what's up with those? I have one of them. I think that was that one, right, Kees?
So the 307s, you mean?
The 307,
yeah.
I think. Yeah.
The
So
307,
without the MP4 compression.
they're actually great. It really depends which one you buy. There are some recommended ones in the wiki, and I bought one of those, and that's fine. And InstaStream is now selling 307s exclusively in their new cameras that are even more sensitive than the old 291s, but they have a separate supplier. I don't think you can buy these on AliExpress, but they're really superior cameras to what
They still have the MP4 compression on the line?
It's still the same type of compression as the H.264, you mean? The same
sorry,
as,
that's one. Yeah.
Yeah, it's still the same thing. It's not raw, unfortunately. It's.
Oh, and that's the 327 that I had, that experiment I did with Kees.
Yeah, the 327. Oh, you mean the MyPi cameras, the one with the cable?
Yeah, the MyPi.
Yeah. So those cameras, as far as I know, I didn't have any time to test any further, but they still do the MJPEG compression. Yeah.
Okay.
Okay, so someone had a question about the MoMet cameras, and yes, they were using the IMX-274s, I believe. They are. Those cameras are much more expensive. The massive cameras, I think they go for like 1,000 euros a piece, and they had a different lens as well, a more expensive lens. However, I think more optimization needs to be done to make these cameras really work well with RMS. In terms of, you know, the ease of use, if I could have chosen what to do, I would actually recommend them just to use the default cameras that everyone uses instead of these more expensive ones. They're yeah. Oh, okay. So any more questions or suggestions? We probably still have about 15 minutes to go in official time, but we can extend it or cut it short however we want. So Kees, you have a question?
Yeah, Dennis, can you tell me a little bit more about drop frames? Because I tried to run several cameras on one laptop with Ubuntu, etc. I used this script from Ed. It was working all well, but I hooked up only 2 cameras, and I saw if I set in the config file the messenger proof report drop frames of true, then I see a lot of drop frames passing by. Is that an issue or not?
So that functionality is no longer relevant for these digital IP cameras. that was actually developed a long time ago for analog cameras. So there's a fundamental difference between how they work. So the analog cameras are going to deliver frames in a specific time window, and if it doesn't get delivered in that time, that frame is dropped and considered dropped. Because it just goes directly from the analog video, it's digitized and directly into the memory of the Pi, right? So it's just a very tight time loop. And if one frame is missing, it means it's dropped. With IP cameras, though, the way frames are delivered, they don't really need to be in a very specific time window. So what happens is that it's, let's say, sending the video frames over the network via your, let's say, router. And what's going to happen is that maybe there's going to be some network on the in the network, or there's something going on, and those frames might be late. So they will not arrive at the right time, but they will still all arrive maybe a bit later. So the way this option counts dropped frames is just trying to figure out if all frames are arriving at the right time. But with IP cameras, that's no longer relevant. However, and also there's a fundamental difference between how IP cameras and all analog cameras work. So analog cameras would just drop a frame, but with IP cameras, because the signal is digital, if you don't send individual frames through the network, you send little packets of data. And if one packet is dropped, you're going to see the frame is corrupted. There's like lines and big blocks and something's going on, right? So it's just like analog and digital TV. It's just a fundamentally different way of like signal, type of signal. So I recommend just don't use that option and it'll be fine. However, you might, if you see like big chunks of the frames missing and like meteors and airplanes, then there are frame drop issues. They're basically caused by the CPU not being able to keep up with the processing, because these cameras send a signal that's compressed and needs to be decompressed so RMS can work with it, right? And the Pi actually uses its graphics processor to do it. And that's why we use the Pi and not some other small, cheaper boards, because they don't have that option. However, if you're using a computer, all that decompression is going to be done on the CPU and probably not on the graphics card. So Pete, you have a comment / question.
Yeah, I just have an observation. It just occurred to me. If we're making time lapse, would there be a way to automate checking the length of the time lapse versus what the total length should be? Because that would identify the gaps in the time lapse and possibly identify issues with the camera, or is something not quite working the way it should.
Yeah, so the way to actually look at the gaps in time, so yeah, that's a great suggestion. So the way FF files work is they take a block of 256 frames and then compress it and timestamp the first frame. And then if you know that your frames per second should be 25 and you have 256 frames, you can work out what the time difference is. And it should be exactly 10.24 seconds. However, if there's some drop frames, there are issues, that time between frames, between FF files is going to be longer. So yeah, plotting up the time between FF files could indicate that there's a problem. So what we could do, yeah, that's a really good comment, is maybe to create another plot that's available in the folder, which would basically be like, what are the average times between FF files and what they should be, like a line, right? And there would be like a kind of, ideally, they would be all like on the line or a slight scatter. But if there are big drops and big differences, that would indicate that something is wrong.
Somebody stated this in an email on group that we may paint such frames on that summary stack of the whole night in red, so that we know that some frames been missed there. Mm-hmm. However, if you miss a single frame per FF, which is not so uncommon, it happens with mostly at the end of the or the beginning of the file of the capture, then everything would be red. So graph stating how much of the time frames are being dropped on the level of test 10 of a single FF file would be much better solution.
Yeah, we can also set like if it's just drops 1 or 2 frames, we don't care. But if it starts dropping more, that could be an issue.
Just a graph stating how much of frames were missing during the night. If it's 1 or 2, then we can live with that. If it's 10, 20, oh. So we can know, and that can be also on a flag for data quality for orbit calculation. If you see some camera has a flag or something like that that drops too many frames, then you may ignore it completely for the calculation of the night.
Yep. Okay, great.
I have one more question about this, Dennis. There's also a relation between, I noticed when I will not do it anymore, switching on is drop frames, but I noticed that if you have a cloudy night, then I see no drop frames. And if I have a clear night, I see a lot of them. Yep. So why is that the relation? Is that the Pi has to do much more computing because you see a lot of stars?
Yeah, so if you said you were running it on sort of 2 cameras on one device, is that right?
No, that's just even on 1 camera, 1 Pi, let's say.
Oh, okay. Well, there shouldn't be any drop frames if things are working well. However, yes, the CPU is doing many more things if the sky is clear. It's basically detecting individual stars, detecting meteors, because it will not even try to detect meteors if it can't detect any stars, right? So if it's cloudy, it's just almost idling.
Yeah.
So there's more work the CPU has to do. Richard, you have a question.
I just have kind of a question. What do you expect to happen over the next 5 years or so when you have new Raspberry Pi, computers coming out? You have new chips, new lenses, new things. When you got new hardware, what do you expect to happen?
Well, we actually went through the exact same process several times already. Buy it, point it to the sky, get some data, calibrate it. If it looks good, use it. Why not? That's it.
I like that kind of approach. Practical. Just try it and see if you like it.
If it works, yeah. I mean, we started with the IMX225. That was the first one that we ever tested. And we pushed that one for a long time, and then it was discontinued. Then we switched to 291, and that seems to still be going. And then the 307 came along, and that one's even better. We also started with a different set of lenses, and we found new lenses that are better and cheaper. They're fine, so why not? If something better comes along, it's great. I mean, if a new Pi comes along that's even faster than this one, I mean, we could use it, although we don't really need to, because the Pi 4 is really fast enough to do anything we want to do, right?
That's exactly, where we sort of jumped from Pi 3 to 4, and we noticed that there's a performance jump. I remember Damir actually sharing, I think it was Geminids or something, picture, and it was the previous model. This is where we started just watching what you guys are doing. We didn't actually adopt RMS fully, but we were just watching what everybody else is doing. And that was the point when we thought, these guys are onto something. The future is digital, I actually remember meeting Damir in Poznan.
Yeah.
So that was kind of fun. Long way, huh?
Yeah.
It's almost 10 years ago.
Oh, was it? Oh my God.
You also met Dennis there as well.
I did, yeah, Dennis, yeah.
But he was not looking like this. Neither do I.
I had more hair.
You have a lot more hair, yeah.
That's right.
I put on a couple of pounds.
Yeah.
Get some loose summer, I guess. Yeah, so you can actually read about the history of the Global Meteor Network on our blog, on the GMN website. There's like a blog part where when I used to have more time, I used to write things there, but no longer. And yeah, it just basically started in 2015 when we heard that Sony stopped making CCD chips. And
Oh yeah, this was
so what are we gonna do? We have to find some alternative, right? And we just kept looking. It was actually Mike Hankey was the first one to start using these cheap IP cameras, and it was the IMC in Serbia in 2017 where he showed just the first pictures and like how cheap they were, and initially just didn't look good. It's just looked too pixelated, bad. But then I came home, and the day after I decided, okay, let's just order it just to see if this is any good. And we spent a very long time configuring these cameras so they actually produce good data, to just find the right configuration settings. Because if they're not properly configured, they just don't produce data that is good for meteors. And that's why we, like really forcing the correct configuration. Otherwise, it's just the data is garbage.
And the breakthrough actually happened once we were sure that we found out the way how to address the rolling shutter issue, and that was actually okay. Now we may go. Before that, we couldn't simply know that our results would be okay. So once correction for rolling shutter has been found and applied and tested, then we said, okay, it's a nice way to go. Otherwise, if you don't know what I'm speaking about, there's an article, a paper, I think it's explained in that blog of Dennis's on GMN. Why is that so important?
Yeah, so the major issue with these sensors is that the way the frames are read is they don't read the frame immediately, the whole image, and then store it somewhere. They read it from top and then slowly to the bottom. They're phase shifted. Like this row is read later than this row up here. And then if you have a meteor going down like this, it is going to appear as if the meteor here appeared sooner than it did here. And that messes up the speeds of meteors. So we actually came up with a correction to correct for this effect. Otherwise, it wouldn't work. If you would like to compare speeds between meteors between different stations, they wouldn't match because of the rolling shutter effect. But yeah, it was a long way to come here. Richard, you still have your hand up. Go ahead.
Oh, sorry, no, I wasn't meant to.
Okay, good. Okay, so officially we still have just a few minutes left, but we can stay on if more people want to discuss something. So Paul, go ahead.
I have another question. A while ago on the group list was a message about possible funding.
Mm-hmm.
And I'm in contact with a number of amateurs in like in Cuba and so on. Mm-hmm. And they are interested, but the story is always the same. We would like to have these cameras, but we have no money. We cannot buy them. I have also contact in Morocco, and that would be a nice occasion. But there is the same. So somehow they have the buildings and the institutes where these cameras can be put. They have the people who could care about it. They have internet, they have electricity, that's all no problem. But no money and import limitations, so they cannot just buy abroad like we can do. What's the status of possible funding to put RMS networks in strategic positions?
That's a really good question. So right now we're actually working with trying to secure some funding through one private company where we would make a project that's more geared toward like the global south and working with younger people. So we're preparing this project to be submitted in the next couple of weeks. We're still unsure if we're going to get the money. We're still unsure about the details and everything. But if that goes through, we're going to start a group of people who are interested in that kind of work. Now, in terms of getting funding from some conventional sources, that might be a bit hard, but we can always do something like Patreon. So the GMN has a Patreon account, and we have a couple of donors that every month the GMN gets something like $30, and that's really basic enough just to cover something that happens with the server. I have to pay for some software that's used on the server, to pay for some licenses, and that really just covers the basics. However, if you really want to push the limit higher, I mean, it would be good to get these people around and say, okay, like we're going to do this project with them, and just really create some sort of a crowdfunding campaign or something. If that doesn't work out, I'm just throwing ideas out there. I'm not proposing that I would even do that. I have already too many obligations, but I would love to hear other people's ideas. In case you have your hand up.
Dennis, can you tell me if the Meteor radio meter project is still alive? Because I expect next month some components. They're not easy to find anyway. So I looked at your GitHub page and I ordered everything, just now waiting to arrive. So finally, hopefully next month. But word to continue with that? Is that?
Yeah. So I recently talked to a person, Ari, in Australia, and he got really interested in the project. But I have to touch base with him about what his plans are on that. He's, I believe, a retired electrical engineer and got really interested in the project. So Damir could probably provide more details, but he has a friend who was working on the project and then got really busy and basically had to drop everything. We're still very interested in making some sort of a prototype of a meteor radiometer that anyone can put together, which would supplement fireball observations through video methods, right?
Exactly so. Exactly so. It is a part that we are missing because we should obtain a significant amount of important data on fireballs. Radiometer, as well as the infrasound detector, infrasound sensor, being prepared by a friend of mine, which is actually overwhelmed with the job in company he works in, and actually I have to ping him back and to check out for the status. Last thing I know, it's okay from last autumn, 3 or 4 months ago. There were still issues with some components and actually with the delivering stuff from China, because he ordered something, then pieces didn't come, then reordered them back, and then okay, bunch of problems. Hopefully it will be working. The point is that he developed 2 really high quality devices, but to have them really tested and so on, we are simply not at this stage at this moment. However, we do have some initial versions of radiometer, like we published something about them. I think Dennis should have one somewhere.
Yeah, we have one running here. So for people who don't know what we're talking about, there is a big problem when we have a bright fireball. It just saturates the image and we can't really know what its real brightness was. And the total magnitude of a fireball can be used to determine the initial mass. So for example, if you remember my initial talk for Winchcombe, we had a full light curve just because we had free pawn measurements, and we also had a reflection on one of the cameras that I was able to use to reconstruct the full light curve. It was just a chance that it was available. However, to really get real intentional instrumental records, what we do is we would take photodiodes and we would just put them under a dome, and we would sample the photodiodes at 2,000 times a second. And then when a fireball appears, what you would see is basically just a brightening above the background, and then it goes down. It's not really important to like have a camera to see the fireball. It's just to have a total estimate of the light that it left in the sky. So the idea was that we would develop something cheap with the price of like an RMS camera that anyone could do, and really it would be possible to connect this radiometer probably on the same Pi that's running the camera. But the project really needs someone who knows a thing or two about electrical engineering and has time to really work on this, and also includes a bit of programming. So Fiacre has his hand up, so if you want to say something, go ahead.
Yeah, just about the radio project. I'm just wondering how you guys are, what's actually emitting the radio waves? Are the meteors themselves emitting the radio waves?
They're not radio waves. It's actually light. It's called a radiometer because a radiometer is a device that just measures electric radiation, but it just electromagnetic waves, right? But it's just light in this sense. Yeah.
It will be high sample rate.
It's a photometer.
Photometer.
Yeah. Yeah.
Sounds better than Meteor radio meter. Meteor, whatever. I will build one now as soon as I have the components.
We haven't invented this. The name is already known, so we have to stick with that.
Oh, okay.
Yeah.
We live with it. No problem.
These types of devices already exist, and I believe the one that's currently deployed costs about $50,000. And we're trying to do it for $100, $200. So it is possible. We just need someone to do it. I see that Derek has his hand up. Derek, go ahead.
Yeah, look, you're out of time, Dennis, but I'm just interested. We're interested in working with schools here. Yep. And I would be interested if there's anybody in Europe that's working in schools, if you could contact me on the forum. But I won't take any of your time now.
Okay, yeah, sounds good. We actually formed a separate group about this, so I might actually send you an invite there. We have kind of an idea that students around the world would work on some meteor-related projects.
That'd be fantastic. Thanks, Dennis.
Yeah, awesome, no problem. Okay, any more comments and questions? Topics for discussion? Okay, well, it looks like that we ran out of topics for this year's meeting.
Before we leave, Dennis skipped a line in questions and answers. I don't want to remain in depth regarding that. Is that some time ago we have an email regarding astronomical seeing and possibilities to estimate the astronomy seeing using RMS cameras. Well, it cannot be done at the level professional measurements are doing it. What can be done, however, is to estimate is seeing actually turbulences in the air affecting the image quality, good or poor ones, or catastrophic ones. So I got some results of astronomy seeing from La Palma, where we have nearby RMS camera, but it turns out that La Palma is actually not the place where you would like to calibrate your RMS camera regarding seeing, because seeing is almost perfect there. And there are only a couple of nights where seeing is poor enough to be at least detected. However, some correlation exists. Just to shed a bit of light, what is the approach? It is based on the fact that in poor seeing conditions, stars are twinkling a lot. So by detecting the frequency of changing of light in between frame and frame, we can try to estimate if the night is good, or actually that moment the sky is looking good or not. So not to mix astronomy seeing expressed in arc seconds with something we will have on some relative scale. Kind of one would be catastrophic, or 0 would be catastrophic, 10 would be best possible seeing. There are some papers which are stating that this frequency of twinkling is connected with quality of seeing, but I haven't found any relation which can with which I can match our data. However, I have a table where those frequencies are being stated in such comparative way. It is only now that I have some reliable data on seeing from some observatory which is at lower elevation than La Palma is at 2,060 meters above the sea level. So if anybody knows about an observatory, I think it's Armagh or something like that. Armagh is in Ireland, so and they don't have RMS camera. But in UK there are plenty of cameras, and there's a possibility that some of those observatories still is doing seeing measurements. And there are some RMS camera nearby. In such case, we would be able to find a way to estimate the quality of the sky almost real time. Thank you for your time.
Bjarke has his hand up. Go ahead.
No, it's just for information in which way I was trying.
You just you mentioned Armagh, and I believe there is plans to have RMS camera put up in Armagh at some point in the future. I was working with Jonathan Mackey last year, and we were installing the sort of, I know they're not ideal, but the all sky cameras, and one of them is meant to go up to Armagh. We just haven't done it yet, and I think if it goes well and if they put it up there, they'll probably want to put up one of the pointed cameras as well.
I recall they were doing some measurements in the past regarding astronomical seeing, but I don't know if they are still working on them. So in case you are in contact with them, perhaps it wouldn't be a waste of your time to mention it to them as a possibility, just to do some exploration, because I think it can be done.
Okay.
It's not only because I think it can be done. We can discuss it and then try it.
Fair enough. I'll mention it to people that I know and see if they'll pass it along.
Okay.
Awesome. Okay. Any more topics for discussion? The seeing thing is definitely interesting, and it's one of the many things that we can do with these cameras, that we just found a very easy way to put, to have pixels on the sky, and the possibilities of, tracking satellites and bird migrations or whatever are really, really infinite. A final call for a topic of discussion. If not, we can conclude the first session of our meeting. Okay, well, thank you all for coming.
Thank you.
It was wonderful to see you all. Well, at least once a year. It was great. And if if it's really late and you want to stay up for the second session, it's going to happen in about less than 3 hours, and then we're going to talk to our people, our friends and collaborators from Australia, New Zealand, the Pacific region, and et cetera, et cetera. Okay, well, thank you all for coming, and see you guys next year. Bye.
Thank you. Bye-bye.